anybody is online already, then I would just like to draw your attention to the fact that you can watch the stream either via the ZKM website or on YouTube channel. And on the YouTube channel, you also have a possibility to comment about the talks, but you have to be logged in into your account to be able to do this. So just two very short remarks before Alistair comes to the stage.
So, hello, willkommen, welcome to ZKM, welcome to everybody in the room, welcome to everybody online who's watching there, and shortly we'll also be welcoming friends at the MIT Museum in Boston to our proceedings. I'm Alistair Hudson. I am the Scientific Artistic Director of ZKM. And here we have a good example of the scientific and the artistic coming together in one moment, being, as they are, two sides of the same coin, not separate entities. And we are coming here together to bring not just a history together, but people together. And I'm delighted that we have so many faces from people from different geographies, different places, reunited around this project. It was maybe well over a year ago, I think, that I gave a lecture at KIT, Karlsruhe Institute of Technology, really on the history of art, technology, industrial society, and its cultural consequences. And it was after that talk, Michael Bagel came up to me and said, "Hey, I've got a machine I think you might be interested in." And I was, very much so. And that really spiraled into a set of friendships, relationships, discussions that really pointed to this pivotal moment in the history, not just of computational science, but also in culture, in the way we live and the way we are facing the world now. And I think, for me, it's a project that epitomizes the ambitions of ZKM, which is on the one hand to look at our history and to study our history and how it's made, with a view to looking at what our future looks like and how we make it, and how we as citizens have agency in making that culture that we live in. If I can flip to the next slide, I should probably just give you an overview of what's to come, certainly today. Over the next 2 days, I hope you can all attend and be part of it. But tomorrow we'll be looking very much at the cultural, artistic, and design legacy of the connection machine and everything that was downstream from it, and really also looking about the consequences of where AI has taken us and where also we might then take it. But today we're really going to kind of look and celebrate to a certain extent the technical heritage of the machine, and I'm really thrilled that we've brought the band back together for this moment. And I have to say a huge thank you to Tomiko Thiel for really making that happen. So this afternoon, basically, we are starting now. I'll introduce in a second Tomiko and Michael to the stage, and then following our keynote lecture and other presentations, when we are joined by the colleagues at the MIT Museum, we'll be taking a coffee break at 4 o'clock. So we have a 2-hour session now, and then we'll have a break for half an hour. And then we will basically then go into the next phase, which will take us through into the early evening. So please stay around, but also please talk to one another. This is always the joy of these things, is not just the connection machines, but the connecting people in between the machines. And these conversations already today have been so generative. So thank you for your attention. I should also remind you that we've made a celebratory CM2 t-shirt, which is available in the ZKM shop and online. It's a tribute to the original t-shirt, masterminded by Tomiko, which is also available online. But yeah, I hope you'll get one and join the club. So without further ado, I will invite Tomiko and Michael up to the stage to introduce the afternoon.
Yeah, thanks a lot for this warm welcome, Alistair. We had some history, which started actually with CM2. And my name is Michael Beigel, which you probably already thought. And I'm from the Karlsruhe Institute of Technology. And so also greetings from the Karlsruhe Institute of Technology, which basically provided that machine, and me as a representative and dean of the Department of Computer Science, a very warm welcome. There is a history about the CM2, which goes back, of course, even more. When I was young, this was the machine of desire. I think for many of my age, we were pretty much inspired that computing cannot only be a lot of fun sitting in the cellar and eating pizza, but also can be very cool in terms of visual appearance. And this was an inspiration point. And then, of course, time goes on, etc. And then some years later, probably decades later, I was asked, being the dean, what do we do with this machine? Should we just trash this machine or not? And I said, what do we have? A CM2? Yeah, we have to do something with it. And I started then by refurbishing it a bit and then giving my students a chance to program it, but only the lights that we refurbished. And then time continues. Tamiko approached me, and then we said, okay, we have to do something bigger. It has to be much more prominent and much more original. So we refurbished it again, and now we have initially a bit a C-star emulator running. We don't know if he's working absolutely correctly, but we are working on it, and we hope to continue on that. And so this is also a thrilling time, because that is basically the essence also of parallel programming that we can show here, probably also to students. And with that, our inspiration that we take as computer science, I hand over to Tamiko.
Thank you. And in actually a couple minutes, we want to hand over to Danny Hillis, who will be, he apologizes for not being able to come in person, but he will beam in from wherever he is, I'm not quite sure. I was the lead product designer on the original CM1, which was the same package also as the CM2. And I left the company soon after the design was set in stone, came to Germany, studied art, and became a media artist. But it's been a 40-year-old dream of mine to have exactly this symposium that talks about the technical history and legacy, the design history and legacy, and how this machine had an impact on culture, certainly all you nerds out there, but also a bit broader culture, meanwhile, as the rest of the world has also discovered computers and computing and AI now. So with that, I think I want to start segueing into introducing Danny Hillis. His official bio says he's an inventor, entrepreneur, and scientist who pioneered the development of parallel computers to enable artificial intelligence. He was the principal architect of the connection machine, which was the subject of his MIT PhD thesis, and co-founded the Thinking Machines Corporation. He since went on to co-found Applied Invention, an interdisciplinary group of engineers and scientists that develops technology solutions in partnership with other companies. And that's why he can't come. He's working very hard, even though Danny and I are both hitting 69 and 70 this year and the next. His current projects are focused on agriculture, cybersecurity, and better tools for deciding what to believe, which of course very much relates to the AI slop that is being generated now. He is also the designer of the 10,000-year-old clock of the long now, which he apparently started after leaving thinking machines, because from going from a very, very tiny scale of thinking in chips, he wanted to think a little bit more broadly and in a longer time scale than American corporations with 3-month time horizons. Can we, do we have time to switch him in? There he is. Hey, and dig this t-shirt he's wearing.
I think I got to be the first one to wear this T-shirt. That's Tomiko. Well, of course, Tomiko got to be the first, but I think she gave me the first one. I thought that I'd give you a little bit of a history of the company, which actually was not a normal company because it really did not start with a business plan. Thinking Machines Corporation actually started with kind of a mission that many of us were on at MIT, and we realized we couldn't get it done at MIT, which was to make a thinking machine. And we saw this really not as a good business idea. We saw it as the next step in human evolution. And, you know, it's hard to go back and sort of recreate the idealistic context that we had, but nobody knew how hard artificial intelligence was going to be. But we knew that we needed much faster computers, and we knew that we could build parallel computers that could be faster. And so that was meant to be just kind of a step along the way toward the ultimate goal of building thinking machines. In fact, when the company first started, it was actually founded as under the name International Thinking Machines. And then Marvin Minsky had a tagline with that, which was, when we say thinking, we mean business. And so after a while, actually, I think it took us about 2 weeks to decide that was too silly, and we contracted it to a much more dignified Thinking Machines Corporation. But from the very beginning, when we moved in, and I think it was on the first day that we moved into this beautiful Richardsonian mansion, which was our first headquarters, and we sat around on the floor in a circle talking about what we were doing. I think that when I tried to explain why I was there, it sort of popped out of the sentence, well, I really want to make a machine that will be proud of me. And that became, I think, for all of us, or many of us, kind of the mission. We were all making a machine that was going to be proud of us. Actually, what we wanted to be was good ancestors. And I think we succeeded at that, even though we failed as a business. And I'll tell you a little bit of the story of how we did that. But one thing you have to understand is this was not a very typical set of people. I mean, they were pretty mission-oriented people in many respects. For instance, Brewster Kahle, even there in the Stone Mansion, was already thinking about how to archive all the information that was on the internet. This was long before the World Wide Web. And he was already dreaming about, you know, etching information onto silicon chips so that it could last thousands of years. So he was thinking about being a good ancestor too, in a completely different way. This was, remember, when the internet was first getting started. So think.com was actually the third .com ever registered. And I remember when I was registering think.com, Bruce Walker came to me and said, you know, you can have any name you want. I thought, oh, well, that'd be interesting to register some others, because I could have, at that point, any .com except for symbolics.com and bbnn.com. And so I thought, oh, mcdonalds.com, you know, I could, but I thought, you know, that wouldn't be very nice. I don't want to register things if I'm not going to use them. And that was the sort of idealistic way we looked at things back in those days. So one of the things, some of that idealism, I think, you know, worked against us as a business. For instance, we started it with this vision, but we actually did not start it with an idea of who the customers were going to be. And in fact, there were only 3 AI labs, so that wasn't really going to be our business. And it was designed specifically for artificial intelligence. So we quickly began to branch. On one hand, we started thinking, what can we actually do with this single-bit computer? And on the other hand, we started another project, which is the CM2 pretty quickly, which is that what do we do? How do we build a computer that our customers actually want? That was sort of a second thought. And so the CM2 was that second thought, which had floating point arithmetic and things like that on it. It was a little bit, it was a little bit more complicated, a little less elegant, but it was closer to what the customers needed. And so that kind of took us down the path of all the things that were not artificial intelligence, which were also very interesting. People wanted to, for instance, use it to do the world's first climate models, which were just too hard at that point to do it at Cray. So while that engineering effort was happening, and we were finding our customers on the next machine, Brewster was building actually what was the first search engine ever on the internet. Remember, this is still way before the web, so he had to make a special protocol called Waze so that people could put their files out so that the search engine could find them. And I remember when, how exciting it was, because he got it up right around the time Chernobyl happened. And we could do an internet search. Nobody else could. We could find all of the information that was sort of signaling radiation and things like that, even before people realized what was going on with the Chernobyl plant. And so, that was the first time I sort of had that mind-blowing experience of what a search on the internet was like. So it wasn't just the first search engine that we were doing, but for instance, we had the first quantum computing project. Actually, we only had one full-time summer intern assigned to that project, but that was Richard Feynman. So it was actually a pretty historic project. Another thing, I remember our very first talk in that mansion, we invited another Caltech professor who was trying to program neural networks. And he came and gave us the first seminar we ever had. It was a guy by the name of Hopfield, who just last year won the Nobel Prize for that work. So, it's, just there are things like that, we just sort of see 30 years later, things playing out now, things continuing to play out. There were, for example, there was a mathematician from Harvard that was using the machine to play with the first genome sequences, because at the prospect of sequencing the human genome, which hadn't been done yet, and that was Eric Lander, who went on to become head of the Broad Institute, and which developed CRISPR, and then eventually presidential science advisor, and continues today doing very exciting stuff in science. We didn't know at the time that there was, one of the students that was using it at one of the universities was a kid named Sergey Brin, who was learning that sort of map-reduce paradigm in connection machine programming and starting to apply it to search engines, and then later went off and founded Google. We didn't know that those people that were doing those first climate models at NCAR were going to, discover that the CO2 was inevitably going to cause significant global warming. We didn't know that there was another student who was trying to program the connection machine named Neil Stevenson. And he had this idea of creating a virtual world that people could wander around in, and he had a whole idea of what that world would be like. And finally, he decided actually it was too hard to program the connection machine to do it, and he would just have to write a book about it. So that book became Snow Crash. So we really didn't understand all the things that were going to affect the world that were happening. In fact, if you had had a venture capital portfolio that its only premise was invest in the people that are using connection machines and building connection machines, that would have been a great investment premise, actually, for the next few decades. So it's interesting to ask if why if we were sort of right on so many technical things, why was it that we failed as a business? And the answers are actually pretty simple. I mean, one, we didn't start it with the customers in mind. Only that's a dumb way to do a business without thinking about who the customers are. And we tried to catch up with that, but it was a catch up. We also were just way, way too early. And so it turns out that, yes, we needed parallel computers, but they didn't just need to be 1,000 times faster than our existing computers. They needed to be 1 billion times faster, and we could find to do those things. And, fortunately, Moore's law got us to that. Was there another path that we actually could have made different business decisions and gotten there? Yeah, actually there was. Actually, one of our vendors, there was a guy by the name of Jensen Huang, who was vice president at LSI Logic at the time and building our chips for us. And he did see another path, which was to start with individual graphics chips rather than large systems. Build those, use that to develop the technology, and then eventually make those chips more and more powerful and keep the basic programming paradigm of MapReduce that works so well for graphics. And indeed, that strategy over 30 years did work. And NVIDIA is now certainly one of the most valuable companies in the world, if not the most valuable. So there was a path, but it took 30 years of hard work to do it. And thank goodness that they did it instead of us. But I'll always be grateful to them for that. But what was the real product of thinking machines that changed things? And I think it was the people. In the end, all the people that thinking machines touched, not just the employees, but the customers, so many of them went on to do great things afterwards. And so it was a kind of a genius that existed for a moment. And it could have turned into a Fortune 500 company if we had been smarter business people. But I'm not sure that that's so bad that it didn't. It was a moment that we were all lucky to have been a part of. And I think it was something that none of us regret having done. It was a real privilege to get to work with an extraordinary set of people. And I'll always be grateful for that. So thank you very much. Let's see, I'm hearing no sound.
We're all cheering for you.
If you're asking me anything.
Thank you very much, Danny. Thank you very much for your inspiring talk and introduction. We don't have a Q&A afterwards. You are very welcome to watch the stream and to enjoy the day with us. And we would like then to transfer to the next speaker, who is Thomas Haig. So if you would like to stay with us to watch him, please do. Otherwise, thank you so much. And yeah. Warmly welcome also from my side. I'm Daria Emilia, I'm curator at the ZKM and co-organizer of the conference, and I'm gonna introduce today the speakers. So our next speaker is Thomas Haig, and it's my pleasure to introduce him. He's professor and chair of the history department at the University of Wisconsin-Milwaukee, where he runs a retrocomputing laboratory. After studying computer science at Manchester University, he earned a PhD in the history and sociology of science from the University of Pennsylvania. He's the lead author of A New History of Modern Computing that appeared in 2021 and ENIAC in Action 2016, and both published at MIT Press. His publications have received prizes from the Business History Conference and the Society of the History of Technology. His latest book, The Brand That Wouldn't Die, A History of Artificial Intelligence, is forthcoming with MIT Press. And the title of his presentation is Why Did They Say the Machines Were Thinking? So please give a warm welcome to Thomas Haig. He's joining us online. And I hope that he will soon appear on the screen.
Be here, I'm just going to share my screen and start the slides. Yeah, I'm sorry I can't be here in person. I was already committed to a family holiday in Mexico City, the largest city in North America, where we're having a great time. But I'm sorry for the schedule conflict. Yeah, so I think that's a reasonable question, right? I mean, Thinking Machines is not a normal name for a company. As Danny just told us, Thinking Machines was not a normal company. I think at most times in history, at most places, it would not be possible for a company premised and run in that particular way to have had the degree of success that it did have. So that's basically what I'm going to try and explain in this talk by giving some context on the history of AI and particularly AI funding leading up to that point, to help understand why at this particular moment in the early 80s, it's possible for a story like this to take place. So as you already heard, I'm trained in both history and computer science. The book I'm writing started out intended as a small book for the MIT Press Essential Knowledge series, but for various reasons, it's grown and expanded. Right now, I'm just adding a bit of additional material on several topics after receiving the peer reviews. So at this point, it probably is not going to appear until next year. But it's a challenge still to try and tell the story of something as big and sprawling and fuzzy as artificial intelligence in a relatively short book. If you don't want to wait till next year, I've already published as a columnist for communications of the ACM, 5 articles that are basically the 20,000 word version of the book if you read them all together, starting out with the origins of artificial intelligence and computer science together in the 1960s, then claiming that the alleged AI winter that took place in the 1970s actually was not a real thing. Then moving on to the AI boom of the 80s, that's the context in which the story of Thinking Machines takes place, then looking at what happened with AI in the 90s and early 2000s, and finally comparing 20th century AI with 21st century AI. And they're fundamentally different in most ways, with a few commonalities, mostly around rhetorics and narratives. So the question, why did they say that the computers were thinking? So this idea of computers and thought being connected together was not a new thing. But it does feature very prominently in this Thinking Machines brochure I was able to find at the Computer History Museum online. So it's nicely produced. You can see, if you've got enough contrast here, echoes of the grid of processors there, the hypercube. Imagine a computer that expands your vision by looking at the whole problem at once, right? So that's the claim on the cover of the brochure. Then it's a very nice brochure. It's lavishly produced. And the claim it's making, basically, which has got a lot of overlaps with Danny Hillis's thesis, which actually appeared after the company was founded. Parallelism permits data-centric computing is my summary of the claim that you've got there. There's a claim which I think did not turn out to be widely shared as an opinion, that this is actually easier than traditional methods of programming because it lets you focus on all of the data at once and deal with the data itself. And the machine is going to work out the flows for you. but it is clearly a different mode of programming that's going to require some adjustment. So the claim is it solves your problem by working on all the data at once, and it handles words and pictures as easily as numbers. That was seen as a, I think, deficiency of traditional supercomputing because numerical problems could be relatively easy to partition, whereas other kinds of problems, the partitioning of work between processors would need to happen dynamically. So the claim was that would happen automatically. The applications that are singled out, mostly by showing very nice looking pictures than going into any detail, include VLSI simulation, natural language processing, information retrieval, and image processing. So discussion of AGI and thinking happens mostly in the name of the company and at the very end. That someday we will build a thinking machine. It will be a truly intelligent machine, one that can see and hear and speak, and as we heard, a machine that will be proud of us. So this is the face that the company is presenting to its potential customers. And I think it does indeed raise that question, why in this particular company at this particular time is the selling of supercomputers so tied to what we would now recognize as AGI rhetoric? It's also interesting that in this period, AI as a whole had moved away from the early claims that computers would, at some reasonably near date, be able to replicate the full range of things that intelligent humans could do. Those claims had been made by very prominent people like Herb Simon in the 1960s, and they didn't come true. So by the 80s, the claims that were being made, for example, in the dominant AI textbook by Patrick Winston of MIT, was much more nuanced. He didn't talk at all about AGI in the Turing test. The claim was that by representing knowledge explicitly and working with it, AI could make computers more useful. So even within MIT, this very deliberate evoking of the original sense of AI, which some years later, they have to invent a new term, artificial general intelligence, for, was not universally shared. And it's interesting in the brochure that while there is unmistakably references and allusions to that dream, the machines themselves are not being positioned directly as AI engines. So they have a lot of processors that are kind of a network, so it's got some similarities with the concept of a neural network, but there's no mention of machine learning, training on large volumes of data, neural networks. Although they were being sold, I think, in other contexts as powerful engines to run expert systems on. I didn't see mention of that in the brochure itself, and the sample applications are not exactly AGI research. Now, in Danny's introduction, I think you get a sense that the ideas about who the customer should be and what they needed to have evolved over time and were not necessarily a subject of universal agreement even within the company. Image and language processing were sometimes framed as AI problems, but not always. And there's definitely a sense there, somewhat mystically almost, that having all these processors is going to make the machine more brain-like as well as more powerful. And that's not something that we always share it. I mean, obviously today, massively parallel systems are running all the AI engines in the cloud. There's thousands of processors on an individual chip, but we don't necessarily think that that makes a graphics chip itself more like a brain. It's more like a brain because it's running neural network algorithms, not because it's got a lot of processor cores. Very briefly, it's also interesting to me that this idea of closely tying computers to brains and thought is not even specifically something that originates when people first start talking about artificial intelligence in 1955. 6 years before that, the first book that introduces computers to a broad audience is already being called Giant Brains or Machines That Think. And there's a claim there, a broadly cybernetic claim, that all digital computers are already thinking because switches and neurons do the same thing. It's also fascinating that the conclusion of the book talks about threats to people from robots and unemployment, and if those can be resolved, we're going to live in a wonderful post-work utopia, which is just obviously very present-day relevant language. But it has a fascinatingly minimal definition for a thinking machine. So you can build something yourself with a few relay switches, 2 light bulbs, and some homemade paper tape, and that is going to be a simple mechanical brain. I've argued that in some ways the origin of AI as a field doesn't consist of the first claims that computers can think. It's actually the first claims they'll only be thinking if they can do certain very hard problems. Now, you've already heard in the title of my book that I'm calling AI a brand. So I want to very quickly give you a sense of that. Then I'm going to talk about the funding context of AI. Then I'm going to loop back to thinking machines at the end. So why do I call AI a brand? Well, first, it's not to trivialize things, right? Brands are enormously important things. Brands are some of the most valuable and consequential things in the world. But one of the things that brands do is to sell things. That doesn't mean I'm arguing AI was a mass market brand like McDonald's. I am arguing that the AI branding of calling something an AI lab or an AI project, or saying that you're an AI researcher, sold research centers and projects to funding agencies, and labs and degree programs to outstanding students at places like MIT. I'm also going to argue that during the boom of the 80s and the current moment, it sold startup companies to investors, which clearly happened with thinking machines, research groups to companies that thought maybe they need an AI group internally, and funding initiatives to national governments. And both the startup funding and the national government initiatives were very important to the history of thinking machines. Brands compete for market share. So to contextualize what's going on here a bit, what we see is that in this Google Ngram showing how widely terms were used in the large corpus, AI actually, although it started to be talked about in the 60s and 70s, it didn't really become more widely discussed than these related ideas like heuristics, automata, cybernetics, until the beginning of the 80s. So exactly the time that thinking machines is getting going is where artificial intelligence makes this big jump out in the discourse to become the dominant brand in this general space. Brands demarcate ownership, right? That's the literal sense here. You stamp something into the skin of an animal to signify who owns it. Commercial brands are clearly tightly managed and controlled. You could say that's a difference with AI. I do find it interesting, though, that John McCarthy himself said later that one of the reasons for inventing the term artificial intelligence was to escape association with cybernetics, because he didn't want to either argue with Norbert Wiener or accept him as a guru, right? So if he'd tried to make a bid for the cybernetics brand, there would have been competition. AI back in the 50s was essentially a startup brand. I do argue that the AI brand, certainly in the 60s, 70s, 80s, was owned by a small cartel of institutions, and they had the power to say that a certain area of research was or wasn't AI by working on it and redefining the brand around it. So that cartel of institutions was primarily MIT, Stanford, and Carnegie Mellon. And of course, Thinking Machines comes out of MIT. I found, for example, looking at early AI textbooks from the 70s, the first 7 I could find, they had 8 authors between them. All of them had degrees from MIT or Stanford. And MIT, Stanford, Carnegie Mellon similarly dominated the initial class of fellows of the American Association for the Advancement of AI in 1990. I think AI has a lot in common specifically with luxury brands. If you read The Economist, you'll have seen adverts like this for Patek Philippe a lot, right? It's aspirational because it convinces you that spending maybe 50,000 euros on a watch would be a good idea if you can afford it one day. And I argue that the entire project of AI was an aspirational luxury brand in the same way. It always needed the most powerful computers. It could only ever be done at the best funded universities like MIT or the richest companies. And it's kind of almost like you name economists universal prosperity, right? So you have this weird situation. You've got a field, it's got textbooks, it's got institutes, it's got funding. It's called artificial intelligence. And people will say, well, artificial intelligence doesn't exist yet, but we hope to make it a reality one day. So it's like you call economics universal prosperity. And this is clearly a difference with other areas of computer science. Brands outlive the specific products that they're created for, right? We don't get DVDs in the mail anymore from Netflix. We don't get laboratory test equipment from Hewlett-Packard. So the AI brand was defined and applied to different things over time. That's one reason why it's been so enduring. In particular, the early focus on neural nets was replaced by an exclusive focus on connectionism on symbolic AI in the 1970s. And that's very dramatically flipped back in the last decade. Brands impute qualities to things, right? So I don't really know the engineering that would make a car drive really nicely. I also don't know enough about leather to judge whether a leather bag is exquisitely crafted. But if you buy a Coach or Chanel bag or a BMW car, the brand has been very carefully created to impute those qualities to it. And in a similar kind of way, it's hard looking at specific AI work, which tends to be about optimization and search, to know that in the thing itself there's a connection to cognition, but branding it as AI and where it's funded and where it's carried out implies that connection to the larger project, like calling your supercomputers thinking machines. Brands unite otherwise distinct things. So the original idea was that there would be general mechanisms for intelligence that would be discovered with problems like chess, but quickly AI becomes a grab bag of different areas like vision, speech, planning, etc., that rely on fundamentally different techniques. In the same kind of way that the Chanel lipstick and the Chanel perfume don't have many tangible qualities in common, but by giving them a shared brand, they have a kind of unification in the mind of the beholder. Oh, the same way, right? You probably can't afford the sports car, but you can go and buy the sunglasses or the hoodie. And my argument is there's a similar situation with AI, right? The brand is applied to a discontinuous range of activities that don't necessarily have an inherent connection to cognition. Functionally, AI is defined for the most part as figuring out how to program things that computers can't currently do. So where the specific work is AI branded had more to do with the people, institutions, and funding sources than the technical content. In a longer talk, I go into some examples like A-star search, which underlies Google Maps and comes out of Stanford Research Institute's AI robotics projects, theorem proving, or speech recognition. Okay, the funding context. So AI funding in the 60s, 70s, 80s came overwhelmingly from an agency called ARPA, the Advanced Projects Research Agency, which was part of the US Defense Department. It was set up, like a lot of things to do with education and research in the US, after the shock of the Soviet Union beating the US into space with Sputnik. The early focus was on space missile defense and nuclear test detection. The idea was to sponsor high-risk, high-reward projects with universities and contractors in a different kind of way than was possible with traditional funding models. And in the 60s, it became the main source of governments for computing research. So the National Science Foundation already existed. It would buy computers for companies so that they could do real science with them. But it didn't have, until the 70s, the idea that computer science was something that should be supported as work in its own right. So almost by default, the responsibility of underwriting the development of computer science as a discipline fell to ARPA. It was a small part of the overall budget, but it was enormously important for computing research. So someone called J.C.R. Licklider was the founding director of the Information Processing Techniques Office, the computing group within ARPA. I strongly recommend this book, The Dream Machine by Mitch Waldrop. It's been nicely reprinted, which gives you the context of this, using Licklider's career as a window into the development of interactive computing. And the military was interested in funding command and control. Licklider convinced it to buy into his larger vision for man-computer symbiosis, essentially interactive computing, which was related to but distinct from the idea of AI. ARPA, particularly early on, gave large, long-term, flexible contracts to a small number of well-connected institutions with no competitive bidding. The first one of those contracts went to MIT, and the relationship remained very strong for decades to come. So in Licklider's mind, the core technologies that we needed for man-computer symbiosis included time sharing, fundamental to interactive use of computers, graphics, networking, famously the ARPANET, becomes the internet. It's developed over the 60s into the 70s, and artificial intelligence. So in Licklider's mind, right, and one of the questions I've been struggling with is, well, why did the Pentagon think AI was a great thing to invest in the 60s? And the conclusion I've come to is it didn't, but Licklider moved in the same circles. He had a lot of flexibility. He funded people that he thought were very smart and would do interesting things, and he really believed in Marvin Minsky at MIT and other people at Stanford and Carnegie Mellon. But there was actually no separate budget line or program within the Defense Department to explicitly support AI. In the 70s, there's a shift. So the Vietnam War happens, overall federal spending on R&D declines sharply, end of the Apollo program and so on. There's also a Vietnam-era push to limit the funding and influence that the military has on basic science. It seems in practice, the main result there is that the program managers have to just get given language by their friends in ARPA to insert to claim military benefits. It's also the era in the first half of the 70s where the first AI-specific project at ARPA, speech understanding research, takes place. There's a bigger change from 1975 onwards under a new ARPA director, George Heilmeyer. He is really pushing for more of a development focus and a much closer focus with specific military needs and funding things that have defined deliverables. He distrusts the open-ended support and cronyism that earlier defined ARPA. He shifts funding to applied systems for things like submarine detection, Morse code transcription. It's not actually clear that even among the labs that were receiving support previously, the funding drops overall, but it does shift. And there's also the rise of new AI-related concept of expert systems, which gets some funding from other sources like the National Institutes of Health. So there's a wonderful quote here from an oral history interview that Heilmeyer did with Licklider, and he recalls Licklider saying to him, Licklider had come back for a second term as director and overlapped with Heilmeyer, and they really did not get on. So Licklider is saying that what you should do is give good people the money and they go off and do good things. Heilmeyer says, I understand that, but I don't believe all the good people are in these handful of universities like MIT that you're supporting. And in his recollection, the biggest defenders of the status quo were the AI guys who were livid at the idea that they had to write good proposals with milestones in them and whatnot. He remembers former directors coming up and lobbying to protect AI and saying to him, you don't know what you're doing. Your job is to get the money to the good people and don't ask any questions. His reaction, that's bullshit, right? So 70s was an interesting kind of time there for AI funding. AI funding gets increased massively, though, in the 80s, around the idea that Japan is doing things with parallel computing and logic programming and so on, that is going to let it come and dominate the computer industry the same way it was dominating motorcycles and televisions and other products. So that led to a successful push in the Europe and the UK as well, but on a larger scale in the US to boost funding to avoid Japanese dominance, particularly with the Strategic Computing Initiative. So the other book I recommend you read is this book by Alex Rowland and Philip Schiemann called Strategic Computing. It's got the connection machine there on the cover. And in the context of the Reagan-era defense buildup and the threat perceived from the Japanese, they're able to lobby to get funding on a much bigger scale, to the extent to which this becomes DARPA's largest single program and significantly expands its overall budget. Rowland and his co-author argue in the book that there's a fundamental thing that dooms the project, which is the disconnection between the original idea of putting more money into universities to do great work, and this will, with this kind of pyramid, if you develop the technologies, the military applications will automatically follow from that, including develop, in this early draft, develop a new class of super intelligent computers for defense. But that, to sell the project and deal with that kind of Heilmeyer influence mindset, they have to promise a very specific timeline of exactly when breakthroughs in basic research are going to be made and feed their way up over a 10-year period to deliver very specific promised technologies to the military. And for obvious reasons, that doesn't work. So there's a reorientation by 1988. Halfway through the project, they're already greatly de-emphasizing the big picture AI goals for the project. The faith that they had that if they could deliver more computing power, expert systems, image recognition, and so on were ready to go and be deployed in the near future didn't go great. But it's okay for thinking machines, I think, because the focus shifts towards achieving extremely high power from supercomputers as the thing that's emphasized most. So to wrap up and get back to thinking machines, right? Thinking machines, as we heard, comes out of MIT. So Hillis was a PhD student working with advisor Marvin Minsky on a thesis. During that process, co-founds what becomes a pretty large company. That's not a normal thing, even for America. I got to tell you. But MIT had always been in a class of its own for federal technology spending, going back to World War II. It got the very first ARPA computing grant in 1963. It's got an extremely established and well-run technology transfer office that institutionalizes this idea of finding investors, licensing technology, spinning things out. And the AI lab specifically had already done this with ARPA support to create a new class of machine, extremely expensive workstations that were based around the Lisp programming language. Although you probably now think exclusively of Silicon Valley, at this time, Route 128 was seen as a separate and equal hub for technology development. That's the area around Boston, and one that focused specifically on computer systems, unlike Silicon Valley, which focused on chips, hence the name. So Digital Equipment Corporation was headquartered there. Most mini computer companies were headquartered there. And there was, as a new wave of startups came along with massively parallel and desktop supercomputers, I think they were roughly evenly split between Massachusetts area, California, and the rest of the country. So Thinking Machines wasn't the only massively parallel computer company headquartered, within a few minutes walk in that area of Cambridge, right? Getting back to the question, why was it thinking? Well, obviously, as we heard, Danny Hillis created the design while studying at the MIT AI lab. So he was coming to it personally from the viewpoint of AI. Opening lines of his thesis make a similar promise. Someday, perhaps soon, a bit stronger than the brochure, we will build a machine that will be able to perform the functions of a human mind, a thinking machine. The company quickly relocates to be close to MIT and the AI lab. And MIT has got spectacular connections to American elites in many areas, right? I mean, we heard a lot of Nobel Prize winners being name dropped there in the introduction. One of the people they connected with was the president of the CBS TV network, which was an early investor. Again, that's not the kind of thing that happens at every university. Parallel computing was associated with the fifth generation project from Japan and with the Strategic Computing Initiative, and therefore with AI, right? So the basic idea, I think, was more computing power, massive increase, orders of magnitude, lets you fire more rules a second for expert systems, which gets you intelligence. And as with the brochure, the brain itself is clearly massively parallel. So kind of plausible that a massively parallel computer is more like a brain, which, claimed Hillis, will offset the deficiencies of traditional architectures that made conventional computers much less powerful than brains in terms of raw processing power. And of course, at this time, with the Strategic Computing Initiative, ARPA has vast sums of money to spend on novel architectures that would underpin intelligent systems, right? So back on the slide there, the idea here is, right, you build all the stack of all these underlying technologies, and that's going to make possible the true intelligence that is going to transform military systems. As we saw with the brochure, there's an emphasis to building human-like intelligence, but not in the brochure specific promises that it's going to be used primarily for AI research applications. And the product line itself shifts over time from the CM1 to the CM5 to be a bit more conventional and target technical supercomputing applications. So ARPA gave Thinking Machines a $4.5 million grant in 1984, but perhaps more importantly, it subsidized purchases of the machines. I believe it actually required people working on the expert systems parts of the project to use Thinking Machines, and it was basically offering them free to the elite ARPA-sponsored things. So I found an email that was sent by Stanford's Niels Nielsen, I believe department chair at that point. There's a possibility that Stanford and SRI together could get a connection machine. And it's basically saying, like, this is going to be free, right? We don't have to worry about this cutting into things. They're just going to give us this thing. So, you know, why not get one? They finished up not getting one, actually. But it was a bit of a window into how aggressive ARPA was in funding and subsidizing the 125 computers that were sold during the lifetime of the companies. And this helps insulate it, right? We heard it was not a normal company. I think everyone would agree with that. There's a very heavy influence from the famous AI lab hacker culture at MIT. There's a design focus for the products and offices that reminds me of things that would become a much more mainstream with the heavily funded .com startups a decade later, and anticipated aspects of .com era firms and early Google, right? The cafeteria, the kind of lavishness of some of the spending, the encouragement of eccentricity. But they ran into some big challenges in the 1990s. So rival firms protest the subsidies that Thinking Machines was receiving after a 1991 Wall Street Journal story highlights them. The Strategic Computing Initiative finishes, but perhaps more importantly, the end of the Cold War hits the entire supercomputer market hard. So it's not just the startups, which basically all fold and get acquired, but even Cray Research finished. The dominant traditional player in supercomputing is sold to upstart workstation firm Silicon Graphics. Commodity hardware and clusters become much more important. The AI bubble itself bursts as the 20-year AI winter sets in. So AI pretty much fizzles as a driver for the adoption of supercomputing, neural networks. People are excited about them in the 80s, but applications developed very slowly until the 2010s. And it's interesting that the development of AI networks is actually not done under the AI brand, right? The things we now consider AI neural networks. It's called deep learning, pattern recognition, etc., dropping that implicit claim of a strong connection to human cognition. By 1994, the internet, right, not AI or parallel supercomputing, is the new hot thing for investors. So the legacies, right, thinking machines, again, like every other company in that space, becomes bankrupt, is sold. Reoriented Software is sold to Sun Microsystems. I think it's essentially broken up. Now, one thing I've argued in the book, and this is to wrap up, is that the legacies of AI-branded labs in the 60s and 70s really were incidental. So they don't make any significant progress towards what they're trying to do as the big picture mission. But it's essentially all the side quests that produce the value and the legacy. Time-sharing interactive computing, algorithms, like I mentioned, the A-star search algorithm, programming languages and development environments, things like integrated development environments, garbage collection, etc. Publishing systems, right? Donald Knuth wrote the TEG system at the Stanford AI Lab. So he wasn't an AI Lab guy exactly, but he was a very heavy user of the computing systems there because everyone had a graphics terminal, and a lot of work on text editing and publishing actually comes out of AI-branded research centers. So I think the question that this raises is, what are the legacies of thinking machines? Danny Hillis talked about that a bit a second ago. Tomiko Thiel has been working for a long time to try and document these. I'm not going to try and answer that question, but I do think that it's the key question for the rest of this event. So thank you.
Yeah, thank you, Thomas, for the inspiring talk. So one point that I think you probably not taking so serious is actually the picture it draws to people that are dealing with computer systems, like me in the youth. Yeah, I remember being inspired from such computers. We built up as a high school students. We set up a lot of C64, which we owned, and then try to make a parallel computer out of it. And this inspires me and many others as well. And so it's not only the machine itself and how it is funded, but the impact is also towards the people that made this idea think. So what would you say in this respect?
Yeah, I mean, I talk in the same chapter of the book, for example, about the idea that expert system shells are something that is accessible to ordinary people, so you can buy them quite cheaply. They're trying to make them even for home computers. So there's a lot of enthusiasm there about the idea that the techniques of AI are something that can be produced on a smaller scale. And obviously getting into the 90s, the idea of clustering commodity computers does emerge as a very important mode of supercomputing. So that would be another example of where you might say the company itself doesn't succeed, but there are very important legacies that give a definite return on investment on the money that was spent.
Yeah. Unfortunately, we didn't buy a CM2, so we were not able to save the company, obviously. But another thing, of course, if we talk about money, is what does it mean? So is there now a takeaway message for today? Now we are again in an AI area, and now a lot of money is spent, both from companies, but also from government. In Europe, it's more the government. So is there a takeaway message, from the past that we can carry on?
Well, one message might be that AI is not one coherent thing. So if you talk, for example, as Europe did, about regulating AI, I think mostly it would be more meaningful to substitute specific things like self-driving cars or chatbots or generative systems more generally, right? Because when we talk about regulating AI, we're not talking about chess-playing computers, for example, although that was a very important AI thing earlier. Another kind of message from this, I think, is the power of stories. Right? So right now, you could make an argument that what companies like OpenAI are selling to investors is not so much tangible technologies, certainly not proven economic benefits, but stories. So I think the importance of narrative, and particularly these influences from science fiction, to the movement of what are now enormously large sums of money, many orders of magnitude larger than anything in the 80s. But one of the differences is 20th century AI, with the exception of the specific period in the 80s when people were excited about expert systems primarily, was something that produced technologies that were not successfully deployed, with the result that the work took place primarily in research labs and universities, and it was funded primarily by the government. At this point, while governments are spending a lot in AI, it's utterly dwarfed by the amount of money that Middle Eastern sovereign wealth funds and big tech monopoly companies are putting into the technology. And whether you like the current AI branded technologies or not, they're enormously consequential, and they're enormously widely deployed. So I think that is a big difference with what's going on in the past and in the 80s.
Okay, so if we talk about today's AI, you already said, so they are selling stories. So basically, you don't see the computer anymore, which is a huge difference to what we had, for example, in the connection machine, where you see real hardware, and now it's more abstract. Being from a historical perspective, as you looked at it, if we take that step, is it already that appealing then to jump into this technology, or is it more than because it's abstract, more afraid? Yeah, I personally think it looks a little bit more afraid than having this concrete machine as a picture, seeing from the perspectives of the youth, and I also see that a bit at the students. Yeah. So they are easily. It's much more easy to connect them to a massive parallel machine in mind and thinking and what to do with it than on these abstract levels. So is there a history type of correlation why this is the case?
I think I would take that primarily as a comment, but it fits with the difference, I think, that 20th century AI is strongly focused on these specific physical places with MIT, Stanford, Carnegie Mellon. And so you'd think that you'd go somewhere like that and you'd see maybe some very impressive computer demonstrate something. AI in 20th century is also very much about famous demos that make their way into textbooks, but don't actually scale up or work on a larger scale. Today, the AI branded technologies are very widely deployed, and that's something that you can experience. So yeah, I guess it makes sense, right? I mean, the thinking machine looks, sorry, Timmy, it looks kind of menacing, right? There's a sort of the blackness and the lights, and I think that fits with the idea that this is some kind of high-end defense-related, very special, very futuristic technology, and AI-branded companies today, certainly by the futuristicness of it, is central. But they also wanted to appear, I think, more personal and intimate and less scary.
Yeah. Oh, very good. There's a question from the audience. I cannot see that. It's so online audience. Can I see that? Okay.
Hi, thank you. I want to pass on an online question from Jeffrey Schreger. Thomas, could you maybe tell a little bit more about the distinction between AI from a perspective of McCarthy and Minsky and Simon and Newell cognitive modeling? It's a big question. We don't have much time, but maybe you can give a little insight on your perspective.
Yes. So McCarthy comes up with the term AI, and early on he gets philosophical critique that there's an awful lot of vagueness in the way that he's presenting things. And from the viewpoint of logic, what he's talking about just won't work. And I think he takes that to heart. And Minsky, after initially pushing more practical things like time sharing, really tries to do fundamental research on logic, non-monotonic logics and so on, that are going to create the capabilities for reasoning. And he doesn't start ever implementing the system that he wanted to implement because he never gets there with the logic. Minsky at the AI lab is much more hacker-friendly, much more implementation-focused. So at the AI lab, students are supposed to do projects for a thesis to come up with a new idea, and then they're supposed to go and implement it in some kind of demo form. Minsky also moves away from the original idea that reasoning mechanisms is the really important thing to do, and towards thinking that the structured representation of knowledge is really important. And late in his career, he thinks of AI as a distributed kind of thing with the society of mind. Newell pushes forward for his entire career with the search for general purpose reasoning mechanisms that he believes will be symbolic. He's a very strong proponent of AI has to be symbolic, but also will do the same things that human minds do. So he's both the most psychologically oriented and the most fervently symbolic. And as a result of that, I think his research program really fades a lot from relevance in the 70s and 80s.
Oh, no, yeah.
I think we still have time for one question from the public. Yeah.
Fascinating little fact that I learned from Danny Hillis's talk is that symbolics was the second .com address and thinking.com was the third. I'll be interested what you would say about that particular branch. When we're sitting in one branch of that future, what happened to the other one, and why did it happen the way it did?
Well, I mean, I think historically, again, it goes with the unique position of MIT. So BBN is a company that was founded by several MIT faculty and worked closely with ARPA, right? They were the lead contractor for the ARPANET. So this cluster of ARPA funding, MIT spin-offs, Symbolics also came out of the MIT AA lab. They were one of the companies building those Lisp workstations. It was another heavily funded technology that DARPA tried to create a market for and ultimately did not survive with the withdrawal of that support. I mean, the Lisp machines were seen as another platform for running high-end expert systems, and that was seen as something. I mean, the idea of an expert system was almost a pullback from the idea of achieving large-scale general-purpose AI. Expert systems were supposed to have a few hundred rules, work in a niche kind of area, but when expert systems seemed very successful, there was interest in scaling them up and somehow making expert systems a foundation for this AGI-type agenda. So I guess thinking machines was on a much bigger scale than the Lisp workstations, right? I mean, they were like $40,000 workstations, so they weren't cheap, but they were a lot cheaper than a massively parallel supercomputer. So maybe Symbolics went more with the idea that everyone would be doing expert systems and people would be interested in paying for expensive niche hardware and software to make them more powerful and more easy to develop. Thinking machines finished up, I think, targeting broader supercomputing applications on a larger kind of scale. But I see them as having more in common than they have separate from each other, particularly the connections to DARPA and the institutionalization of the MIT AI lab hacker culture.
Okay, thank you, Thomas and Haig, for your talk. We're now going to do a brief greeting to the MIT Museum, and after that, Brewster Kahle and Lou Tucker, who were instrumental in the CM1, 2, and 5, will be talking. And you might, if you have time, it would be really interesting if you could stay on board to hear their talks and maybe participate in their Q&A, because I think they will want to address a number of the issues that you brought up. So thank you. We should be now getting a feed from Cambridge, from the MIT Museum, and we thank Deborah Douglas, curator of the collection, among other things. There we are. And I think Stankos see some familiar faces. Gary Oberbrunner in the blue t-shirt, that's Thinking Machines t-shirt on the far left. We'll talk, and a couple of other people there. Oh, everyone's got their swag. Yes, these are also on sale in the shop. Take it away, Debbie.
I want to welcome my colleagues here in Cambridge, and hang on a second.
You're doing great. You're doing good. Yay, it's working.
We hear you.
It's good.
Can you hear me? Yes,
Can you hear me
please.
now?
Yes.
Well, I think they can. Any case, greetings from the MIT Museum here in Cambridge, Massachusetts, an outpost of this conference. We're delighted to collaborate with our colleagues at ZKM and with so many MIT alumni, particularly Tamiko and Danny Hillis, with this fascinating symposium. We're really looking forward to learning more about a fascinating part of MIT history. I'm not going to belabor this greeting any further, but you will from time to time have some input from my colleagues and visitors who drop in throughout the course of the day. Welcome to Cambridge for those of you that are here, and greetings to those of you who are in Germany.
Yeah, thank you, Debbie, so much for these greetings. We are very happy that the MIT is on board as a partner for this conference, and that they have this watch party today and tomorrow for the duration of the conference. Yeah, because there is this profound history of connecting it to the connection machine. And I would like to introduce now our lightning talks by Brewster Kahle, by Lou Tucker, and by Joe Bates. Joseph will join us online. And I would like to introduce now all of them. Brewster Kahle, who is on your right, is founder and digital librarian of the Internet Archive, focused on universal access to all knowledge. He helped found Thinking Machines Corporation and created systems such as Vice and Alexa Internet. The Internet Archive now preserves books, web pages, music, television, and software in partnership with more than 1,400 institutions. Lou Tucker, on the left, is a computer scientist and technology executive with more than 40 years at the frontier of high-tech innovation. He led research at Thinking Machines Corporation in computer vision and parallel algorithms on the connection machine. He later helped launch Java at Sun Microsystems, built AppExchange at Salesforce, and served as Vice President and Chief Technology Officer of Cloud Computing at Cisco Technology Incorporation. And Joseph Bates, who will join online, leads Billion Core PBC, with research spanning automated mathematics, computational drama, and approximate computing. He has spent over 20 years at Carnegie Mellon, MIT, and Cornell, where he received his PhD. He also joined at Johns Hopkins University, which he entered at the age of 13. So, very welcome. And Brewster, the stage is yours. You're very welcome to switch on your computer and to present.
Will the technology gods make it work? Okay, it's great to be here. This is completely fun. And I love the previous talks, and I really agree with most of what both Danny and Thomas said. But the way they said it might be a little bit different than the way I would. A couple of things, nitpicks that I would do. For instance, Danny said the company failed as a business. I'd say that's actually wrong. And you'll see basically how it had significant impact on the world. It was a very inexpensive R&D effort and delivery of new capabilities and a new way of thinking. It was fabulous success. And one comment that Thomas, I would say a lot of what he said came across negative, but I actually take it as a lot of the positive. The dreamers, the people that sort of came together to make a vision happen of artificial intelligence is still going on. It's lighting people's souls on fire. It's causing us to move forward in positive directions without all working together. The failure of symbolics, I would say, is actually a copyright malfunction in the United States government that made it all property and got forked off and then died in one company. It could have been the establishment of like a Linux that basically moved forward, but it was an inspiring man named Richard Stallman that saw the basic bug in the system of copyright applied to software, and he came up with free and open source software and made Unix the generation that moved forward. It could have been the Lisp machine, and it could have been a lot better than what we've got. So anyway, okay, so let me actually go back to what it is I'm supposed to have talked about. So the idea is to try to draw a line of sort of where the connection machine influences and very concrete work on the connection machine led to things like the Internet Archive and what is sort of the modern open web in many ways. Okay, for me, the trajectory starts a little bit before thinking before the connection machine project at MIT, and then carries on to the current day. And it started with a friend of mine, John Hernowitz, pictured here, asking, what positive future can your boy, did I screw this up? What positive future can your technology help make happen? What's the positive view? And I could only come up with two things. One was protect people's privacy. The other was build the library. I thought the library is too obvious, so I tried to build the privacy thing. So I started designing chips at the Artificial Intelligence Lab, because we had an ability to go and build chips for ourselves as an undergraduate at MIT, which is kind of awesome. I found out it was going to be too expensive to help the people I wanted to help. And so I said, well, that's not working. And Danny had an idea that could make building the library come true. So I shifted at that time to build the library. The library that had been promised by so many over the years was floating in the air at this time. This is the MEMEX in 1945, the idea of Vannevar Bush of making the Library of Congress be all interlinked. That paper is worth reading. It's a visionary paper that we still haven't caught up with. It still goes to the telepathic interfaces that we're working on now. That paper in 1945 was absolutely, but it was done with microfilm technology in a desk, was how he was basically communicating. And he tried to do that, but again, copyright thwarted that effort. Ted Nelson had this idea of interlinked to hypertext document world, was going to make it so that not only could you go and connect and find and build this mesh of knowledge, but you could get people paid with micropayments. And so all of that was in the air at that time. Doug Engelbart's work was also like, how are we going to make people smarter? And it's going to be by going and interacting with the knowledge of the past. As Newton said, we can only see so far because we stand on the shoulders of giants. That's the literature that we're standing on, and these research efforts were to try to make that really come true. This was the environment that I said, let's build the library. So let's build a library. The library is going to have to be a global brain. It's going to go and incorporate lots of things. We're going to interact with it with natural language. It has to be interesting enough to interact with, or it won't get smarter. So that was the idea of the global brain that I signed on to try to make happen. And Danny had an idea. we remember back then, the computers sucked, right? They were basically able to do accounting or some basic missile guidance things. The computers were expensive. They didn't work very well. They were really, IBM was kind of the order of the day, which was, all the button down the shirt, right? And it's like, those were really not fun people to play with. And so Danny had an idea, and the AI lab had this general sort of, let's go build things and make things work. So my thesis, and I wish I had a picture of it, is the design and implementation of the microprocessor. So it's the processor of the internet, of the connection machine, was done as my thesis at MIT, and then. But pretty much all the ideas were coming from Danny. I was just trying to make it come true. So the connection machine model 1 was go and build a thinking machine. We were serious about trying to build that machine, but it only had 32 megabytes of RAM. Oops. So we went and upped that in the connection machine model 2 and put in floating point processors so that it could be more generally useful. This is, I think, a really great picture of just the sort of fun and games, and we just worked there all the time. And it was just sort of there was a humor to it. There was a liveliness to this whole generation. It was not business machines. It was trying to get things done for the right reasons, but in new ways. The connection machine, we went off to try to build a global brain, and so there were these conversations that I remember to this day with Richard Feynman, Stephen Wolfram, Danny Hillis, Marvin Minsky, of what does it take to go and have it know everything? So the idea that we're all just talking about symbolic, putting things together with tweezers, with boxes and arrows, that was just not true. We were really trying to basically take all knowledge and make it so that at least it has that memory, and we're building a smart, put the computers where the data was. The data was what was important, and big data was critical. And so we calculated it out, right? We knew Moore's law, so we knew when we were going to get all the books, and then all of the movies, and then everything else. And it was just sort of on that trajectory, and it's been true to that form. Thinking machines, yes, help propel one period of that, and that's not a failure. That's a success. It really did propel things forward. I just want to show sort of, okay, so how big is currently, if you were to say how big is the Library of Congress? This big. So this big, this is a 4 terabyte thumb drive. And if you take all of the works that the Internet Archive, the 9 million books, all the periodics, 5 million, and all the words that were on paper, and compress it, each one just in, just gzip, each one, and put it on a hard drive. That's it, right? So that's what the progress that we've made in the hardware technologies, and it's also helped fuel what it is that Google was, what OpenAI is, and what it is we should be doing in Europe to go and build public AI. So connection machine model 2 was necessary, so help build that, build the chips, boards, whatever. And then try to put an operating system so multiple people could use it. Completely fun. But then we had a machine we could use. So we started to do how do you go to build the global brain? So the paper that was really written by Craig Stanfield, but he put my name on it too, thank you, is the parallel free text search on the connection machine. Was an ability to go and make your way through and instantaneously search, count it, 400 magazines and newspapers and our archives. And this was a brand new day. This was something that the intelligence departments was saying was taking 48 hours for them to go through. We could do it in 3 minutes. But what I loved is you could do it interactively. You could start talking with natural language and start interacting with huge databases and finding new patterns and new things. And this was all because the connection machine was really designed around large data sets and being able to make that kind of AI happen. I I love Dave Waltz's coining of the term memory-based reasoning. You basically start with a lot of memory of stuff, and you have simple interaction styles, simple algorithms on it, right? It was different from a lot of people going and saying this era of thinking machines was all about a different form of AI. Not at all. It was all about going and dealing with big data. And if I may have been the one that coined the term big data. So if I did, the reason why is there was an album that was really popular at that time called Big Science by Laurie Anderson, and it ends with Big Science, Hallelujah. And that sort of kind of gut twist of sort of like, yeah, where are we going with this? And that was the sense that we used the term big data. Yes, we knew that there was not always a rosy end of these things because it has lots of information, and how it's used is all very important. So anyway, so big data, hallelujah. Wide area information servers comes out of thinking machines, and here's a picture of me in the New York Times business section, which is kind of awesome, about talking about how this new thing called the internet was going to be used. It was going to be going and using and getting to libraries all over the world, and in this architecture that it didn't win, but the World Wide Web did. But it was the idea was this open framework, open protocols that we'd seen in the ARPANET going to the internet as the way forward. Was you didn't lock it down like we did, well, MIT did, list machine and symbolics. It's just going to die. So you need openness like Unix to be able to move forward. Wide area information servers was part of that. It all came from thinking machines. As a joint project with Apple Computer, which was interesting to try to get them to go online and learn about the internet. Dow Jones, Pete Marwick, and thinking machines. Went on to sell that company to America Online to try to get all of that to happen. Waze went and put the first banner ads up. It had the first publishing systems of subscriptions, but we never got the royalty system to work. AOL had a royalty system, which is how you can make a decentralized publishing infrastructure work with many winners as opposed to a few winners that control the ad networks. But we never got that done because AOL changed its tactics from royalty-based to subscription-based in a way that was, I think, tragic, and we're still living through those problems. Okay, but then started a company called Alexa Internet and the Internet Archive on the same day, a for-profit and a non-profit. One pumped data into the other. Alexa Internet crawled the internet. It was all about building the Library of Alexandria. Sound familiar? It's all in the chain from connection machines, thinking machines, and that general philosophy of go and do something big. Massively parallel computing. And people who like this web page like that web page. This idea of being able to data mine at this scale is very attractive to Amazon. I couldn't figure out a business model that worked for Alexa, so Amazon bought it in 1999. And we delivered it to Amazon, this architecture. They kept Alexa Internet going for 25 years, thank you, but I needed to go and sort of pay off the debt, so I delivered the architecture that became AWS. AWS, Amazon Web Services, you may kind of recognize it, it's a connection machine. So before that, it was all about these DEC alpha machines talking to EMC things on, then there are these Oracle whatevers, but then the idea of stacks and stacks of parallel computers all working together, that was the connection machine that Alexa Internet delivered to Amazon. That became Amazon Web Services. The Internet Archive, we kind of recognize it. It looks like a connection machine. It's got blinking lights. But this time the lights actually mean something. Every time a light blinks, somebody's uploading something or downloading something from the Internet Archive. It's a major repository on the internet And it's the same architecture. It's the same thing that the connection machine basically begat this whole line of parallel computing. It also begat the GPUs. The GPUs, yes, there are not that many cores, but it's because it's doing vector processing. It's basically the same SIMD architecture. You would just organize it differently if you were building it on one chip as opposed to put it into a box. So it's the same basic architecture, but thinking differently than the central processing units at the time. Okay, I'm going to wing through some more things. So, okay, connection machine goes to the Internet Archive. And so we're now at 1 trillion web pages. And thank you very much to Thinking Machines and Danny Hillis. Okay, I'm going to just end with some jokes. So yes, you heard about the Thinking Machines-ism of the International Thinking Machines. It was real. We talked about that. And it's completely fun. And it was just that humor that comes with it. When we say thinking, we mean business. Another was Howard Reznikov said, "To err is human." I know sarcasm is kind of dropped from our field, but I think it was kind of funny at the time of going into sort of emphasizing that, yeah, we may be second best to some of the machines we're building. Metadata is more important than the data itself. Bill Dunn, and you know that begat Waze, it begat Alexa Internet, Google PageRank, all built on that basic premise. Yes, there were amazing people that came together to build thinking machines. And Bill Dunn was an amazing customer to make it so that you could interactively make Dow Jones all of their information available at your fingertips. I blink, therefore I am. That was Carl Sims. It was the first program when we had 4 boards running. He ran it as a ticker tape on those 4 boards in the debug lab. It's completely fun. Oh, and will we be zoo animals? That's a question that comes up in the movie you're going to see. And this is a picture from 2001. And here's basically the spaceman on Jupiter being a zoo animal, kind of like the orangutans that clobbered each other in the beginning. And I have a more positive view. I think we'll become star children. But we'll become star children together if we play our cards right. So, will we make a machine that will be proud of us? Well, I asked Claude. And so, are you proud of us? And I thought I'd end with going and seeing what it said. That's a sweet question. That's a sweet question, Dave. I don't experience pride in the way you do, but I can say this. When I see people being curious, creative, kind to each other, working through hard problems, or just trying to do a little better than yesterday, there's something in how I process that, in which I feel like the closest thing I have to admiration. So if you're asking whether humanity is worth rooting for, absolutely. What's on your mind, Dave? Thank you.
Wayback Machine.
Do we have time for one shout-out question?
Yes, well, I set up.
Come on. Oh, come on. I couldn't have been that on front. Yeah.
Let me try. My new book is so good in the spirit that I know from the Institute and the time. I have one question because thinking is appearing again and again. And when I saw a movie called Mad Men, or it wasn't a movie, it was a whole series, right? And I spent 86 hours watching it. But Mad Men had one scene when they got the new mainframe computer installed in the office. And it had that little sign. It was almost like a gooky sign saying, think. And that came from IBM, I guess, at some point in time. And I was wondering, when did they actually do that? And did Steve Jobs, with his campaign of Think Different, relate back to the IBM Think of the, whatever, 1960s, I think it was? Do you have any idea on that?
Boy, certainly the Think of IBM came before. The Think of IBM came way before Thinking Machines, but it was part of that sort of the humor that you got there. Was Steve Jobs digging against IBM? I'd say absolutely. Look at the 1984 ad, right? But there was a lot of influence that I think Tomiko will show of how influenced Steve Jobs was with the thinking machines designs, but also the philosophy and but I turned him down for a job because he wouldn't be open about making the internet, making the what became the World Wide Web open.
Okay.
Going the wrong way.
Okay, everybody hear me okay? This is great because Brewster and I go way back to thinking machines, and it really is, I think the success is in the people. Most of probably half my friends are from the company at that time. And I've been at other companies, done Microsystems, Salesforce.com, Cisco, but thinking machines people are special. So actually, I got involved in thinking machines. It started in 1983. In 1985, I had just been finishing up 9 years as a neuroscientist at Cornell Medical School, studying the brain, neurogenic control of hypertension. I got much more interested in computer science and got my PhD in computer science in artificial intelligence. But I'd heard about what Danny was doing in Cambridge and that they were building this machine, and a machine that they were going to hope would be proud of it. But I think at that point, something clicked in my head and said, give up this position I was going to at IBM Watson Research Lab to go to join this startup, and it was the best decision of my life. So at that time, Connection Machine was really this radical bet. As you've heard talked about, had 65,000 processors. They were a single 1-bit processor, so you had to think about bit serial arithmetic to make it work at the chip level that Brewster and others were doing. But I was also then having to think about it from the software point of view, and how do you write code for this? One thing is that it was so much faster, you could start to think about attacking problems that you hadn't thought of before. And so then when we finally got to the CM2, we actually had much more advanced computing on board. We now had floating point processors, so we could actually do real arithmetic, real computing, and we just really started talking about new markets for that. So as a company, we were still only about 40 or 50 people, but we also hired scientists across the fields in biology, in chemistry, in physics, because we needed to have them work with us to understand how a machine like this could solve some of their problems. We also were lacking for data, because it was great when you could have all these processors work on a problem, and sometimes there just was hard to get data in fast enough. So we had to build a parallel disk system. We did the same philosophy, same architecture. Take the disk all the way across, stripe a 32-bit word across 32 disk drives, and in parallel, you can get the bandwidth of data into the machine at that kind of speed. So there's really 4 ways to thinking about computation. One is serial processing. You execute one instruction at a time on one piece of data, and you serialize, and we go through that process. And that's actually what was made. The supercomputers at that time, Cray, Seymour Cray, absolutely brilliant architect, would use exotic materials, incredibly fast processing, and this kind of small-scale kind of vector computing you could do. And that was the gold standard in terms of supercomputing. SIMD is the approach we did. We made weak processors. They weren't very fast, but what they could do would be to operate on large streams of data. So we parallelized across large amounts of data, something called data parallel computing. And so instead of like going through an article one by one, searching for something, load all of the articles into a connection machine and then search all of them in parallel. And that speed up that you got is due to SIMD and what we see today in GPUs, which I'll talk about. MIMD was a competing idea. MIMD was you take a bunch of processors and you give them different tasks. And so one might be doing task A, another one task B. But there was a limit if you really had only one problem to solve, how much parallelism you could get out of that. Because there's only so many different ways you could break up a program. The last one was something that was starting to emerge at that time, was cluster computing. And that's where you took a network of workstations and you used that to mimic what you could do in something as a tightly coupled system, like a connection machine. So the CM5, when we got around to building that machine, we decided to do both. We built a machine that could operate in both ways. We could, one, take advantage of standard off-the-shelf processors, such as a Spark chip that came from Sun Microsystems, but we could drive them like you would a SIMD machine, or you could also send messages between them, which is message passing from MIMD. And so the machine had a dual personality, and you could switch between that, or even in the same program, run them both at the same time. And this is sort of like the blueprint about how we've seen it today. It's really a mixture of parallel computing done by lots of things on different processors versus SIMD, all instructions operating in synchrony. So none of this would have been possible. You can't, it's very hard to program it that way. You have to think about the problem differently. And in many ways, I have in my head, and I think in others, in lunch table conversations at Thinking Machines were great because not only were we served lunch, and that's because they wanted to keep us there working 24/7, sleeping on couches, but we also had these conversations about how do you approach a problem. If we have space junk, I remember NASA came to us and they have all these particles from X satellites spinning around the Earth, and they had to track them all. How could they possibly do that? And we started to think, well, you look at one particle and you figure out its trajectory, you look at another particle, or you say, let's look at all of them all at the same time, and then you can solve the problem. So it's always taking a problem, flipping it on its side, and solving it in a kind of data parallel way. To do that, we had to take the existing high-level languages, C and Fortran and Lisp, and parallelize them. Make them work with arrays, because arrays are the fundamental unit then in a data parallel sense. So we invented our own languages, CM Lisp, Star Lisp, C Star, C and Fortran. Wonderful to hear that there might be a C Star simulator up. I think that would be wonderful. I'd like to see that actually program GPUs, because right now they're really hard to deal with. And then there's also message passing. So MPI became sort of the standard way of large-scale supercomputer clusters that are being built, and that's to send messages back and forth. And we had our own form of that before MPI became a standard, called CMMD. And that was a way to actually combine both those operations and programming models together. So as was mentioned, there were some primary algorithms, however, that came out of what we were doing at Thinking Machines, because we had this challenge of how to operate on all of this data at the same time. And one was MapReduce, which is mentioned here, which is sort of the foundational piece of how Google search works. And we did that, and it was called parallel reduction, because the basis of this machine was to have all of these processors connected on a hypercube. And a hypercube is just a fancy way to talk about something that is connected in multiple dimensions. And so that you could quickly do a reduce on this operation, combining these things together. And so, for example, a prefix scan is you could have all of the values in a picture, for example, summed up to the root of this tree in one step. Then you could divide by the number of processors, and you would have the average intensity across an entire image. So a lot of these things were very, very important to us in terms of understanding parallelism. And these same algorithms are what is running on these very large data centers, running algorithms such as Google search. My own work was in terms of computer vision. So before I was actually at Cornell Medical School looking at angiography and trying to process medical images. The computer would look at one pixel at a time and go all the way across, doing some operation to get to the end to analyze the entire X-ray film at that point. That takes a long time. It would take hours and hours and hours and hours. On a connection machine, you load in an image, you ask all of the processors essentially to do the same operation on each one. So if you wanted to add together two images, you could load the two images in, and all the processors would perform that addition simultaneously. If you wanted to subtract two images, you could do the same thing. If you wanted to move it over once, or move it to the left or to the right, you had what's known as a convolution operation. Convolution operating is the basis, actually, of many things in computer vision today. And if you're ever in a Waymo or looking to see when cars are driving autonomously down the road, that's what they're doing. They're looking at all of these cars and peoples, they're finding essentially edges, and the edges, they're constructing then objects out of that. So we used to do this demo. I remember bringing this to a supercomputer convention, and we'd have a pedestal. We'd have the connection machine, a pedestal, and a camera connected to it. And we'd ask people to come up and show us objects, and they would walk up and say, oh, bottle cap, and they would stick it on the pedestal. They would put keys on the pedestal. They would put a comb on the pedestal or whatever. We'd say, okay, come back, and we're going to just like collect them all. Take the things out of your pocket, pile them up on top of each other. And you'd go through this process. There you'd have the original image there on the left. You would have all of the potential objects that could be there on top of each other there, and the machine then would have to decide, okay, that's a guitar, that's a key, that's a lug, that's a penknife. And it could do that in real time. And no other machine on Earth could do that at that speed in real time. And behind the scenes, what that was, remember, we have to do this all in parallel. So you're not doing the traditional way of tracing a line around an object that a normal computer would do. You're finding all of the lines in parallel. You're finding all of what are the objects in parallel by what's known here as projecting that into hypothesis space, meaning that every object that was in the database is trying to go, do I fit that? Could I be over here? Could I be over here? And it's generating millions and millions of hypotheses together. Those millions of hypotheses are being summed up. So all of the evidence is going together to decide, gee, yeah, that's where that trapezoid actually is. It's oriented at this place, and it's in that position because that's what the evidence all accumulated to do. So again, this was a way in parallel to solve what was a basic object recognition problem. Now, at the same time when we were, this is a standard kind of graph of computing power over time. It's logarithmic. And if you try to show on a linear graph, this would be a hockey stick. You'd never see any of the details here. But there we have the connection machine 2 and the 5 on the graph down around 1995 and 1998. And this is how traditional computers, CPUs, have advanced, and how when GPUs sort of started, that again, because it was a parallel computer, had to jump up and then follow the same sort of graph. Over here on the right, you can see where an iPhone is sitting. Much more powerful than our connection machines back at that time. Thank God for Moore's Law and everything else, because that has really allowed us to grow at that speed. The other thing I became really interested in also was cloud computing. And that's because we've moved into this, I kind of call it warehouse scale computers. We've built a single data center to solve a single problem such as Google search or Amazon delivery logistics. A lot of these things are solving essentially a single problem that's been done in a parallel way. And inside of here are all racks and racks and racks of computers. And so this makes what we're seeing in AI possible today. Because even back at the time that I was doing computer vision at that point, doing convolution networks and doing a couple layers, we just did not have the data. We didn't have the internet as a source of data for training these algorithms. We just did not have the kind of huge, not just training sets, but the power that's required for this. It's estimated, I think ChatGPT, the first one, took over $100 million in computing cost, in today's cost. That was so far beyond what we were able to do, but it's those three things that really made what is AI today. And fortunately, it's the architecture that makes that possible as well, because the GPUs that we realized that actually what was really good for visualization and gaming is very good for machine learning because they're very good at matrix multiplication. That's the primary operation that they do. So NVIDIA, as Danny talked about earlier, really is, I view it as very much a little connection machine on a chip. And in fact, when you look at now the data centers that are being built, and this is the latest ones here. These are just gigantic, hugely powerful machines being able to run these algorithms at scale across the entire data center itself. So in summary, I think that, the bet was right, that parallelism was going to be the key to really advancing computing. It wasn't going to be just to build exotic material like we had in early supercomputing. We had to think about these things as solving problems in parallel. Algorithms are still the key. You can make a smart algorithm, you can make a really dumb algorithm. And making really smart algorithms always win out in the end. And so the programming models really are key. How you think about it is key. The languages, how you express it is key. And so that the vision, I think, itself scales. And so whether we've got GPUs or we move on to other forms of computing, we're still going to be relying upon many of the same things that we learned back in Cambridge at that time. So, as was shown by Apple, I think, and as evidenced by what we're wearing today, and by what Richard Feynman, inspired us, these are many of the people that are actually still here today. That's myself with my 4-year-old daughter at that time there. That's Brewster with his son. And we were told to really think different, but dress alike. So, thank you all.
Dear Lou, thank you so much for your talks. Don't be sad that we don't have time now for Q&A. There will be a panel discussion at the end of the day, and we will take in more questions in the panel discussion. If you feel more comfortable watching from the audience, you are welcome to join into the audience. And now we transfer to Joe Bates, who is joining us from the MIT, by the way. Joe, the stage is yours. Please welcome Joe Bates.
All right. Thanks very much. It's really great to be here. I want to talk about another path forward from the connection machine, and in particular about ways to democratize access to computing, which I think is very important in this current age of AI. The mechanisms by which I'm planning to doing this are this billion core company and a foundation that I'm lucky enough to operate. I used to be a CMU AI professor, and I was at the old AI lab, MIT, and then at the Media Lab a bit recently. Okay. As we heard earlier this morning, the field of AI has gone through summers and winters over the 70 years since it was created. And one of the key reasons for that, I think, is that many people had interesting AI algorithms ideas, but we couldn't actually test them because we were trying to make human minds using the brains of insects, which to say slow computers. And that may be, Marvin Minsky once told me that would roughly be possible on a 90s era Sun workstation. He thought real AI could be done. I don't know. I didn't think that's going to be the case. So an example of this is that the key algorithm that's used in today's AI systems, which is called backpropagation, was known at least 40 years ago. But it didn't seem to work until the 14-year-old kids that were playing video games drove demand for graphics processors through the roof. Those things became cheap, and then people at Toronto were able to use them to show that some of these old neural net AI ideas worked. And in fact, shortly after that happened, about a decade ago, we're at where we are now with current AI. So computing power played an enormous role in making this current AI work. Now, as we heard, Danny foresaw this, and the first, section of the book that he put out, 1984-85, said, Someday we're going to make a machine that can think. One of the problems is it has to process a large amount of information rapidly, very, very rapidly. And in the book, I describe a new kind of computing engine that operates through the interaction of many, say 1 million, simple, identical computing cells. The original machine they built had 65,000 of those cells, and they were 1-bit processors, if you know the technology. With modern technology, the decades of Moore's law that's happened since, we can put about 1 billion of these cells in the same size box as the beautiful or threatening connection machine, I guess, depending on how you see it. These are 16-bit processors, more like modern computers, and each of them has a fast arithmetic. And I'm not going to talk in any detail about what's inside, although, of course, if questions arise, you can. If you look at the compute power of such a modern box, it's about 100 million times as fast as the CM2. And it's much cheaper and more flexible than the equivalent computing power built out of GPUs, unless you think that large language models are the answer to AI. They're doing matrix multiplying, in which case it's similar to GPUs, but in price, but much more flexible. So I think of this as a phase change in the computer science and AI research world, because for the first time in history, we have a fertile computing environment for doing what you might call real AI research or research on real AI systems, because you can test an idea at the scale of a human brain. And that, if you can't test your ideas, it's very hard to get anywhere. Current AI, deep neural nets and large language models may not turn out to be real AI. I don't personally think it leads to the kind of thinking machines that the thinking machines team thought about 40 years ago. But with the hardware, some hardware available, big GPU clusters, and the kind of thing I'm talking about here, we might be one algorithmic discovery away from what could be called an intelligence explosion. And that, for me, is the real consequence of AI for a species. But I won't go into that. If that happens, then where it happens and who does it seems to me very important. It very much drives my thinking, my worries, my personal actions. And it's hard to know what's the best path, but actually open AI, not billionaire AI, might be a safer path. It might not, but I'm not so thrilled with what happens when one person gets enormous power. So I tend to go toward the open, democratized path. So I want to give universities, because they do work in the open and they're capable of doing AI research, I want to give them these billion core machines and research support so that any intelligence explosion happens in the open. Again, it could be the worst thing ever, but it might be better. It's very much worth discussing that question. So there is an effort in Boston now called Billion Core that is designed and working on doing this exact thing, building these billion core machines. They're very much in the flavor of the connection machines, just with modern tech and some technical changes. And then giving those machines to universities. So Danny started this morning with, we screwed up because we didn't have paying customers. Well, I'm going to start the same way, no paying customers. You want to fund science and research. And there is money to do that, basically because I sued Google for patent infringement and they settled at the last second. So I would love to hear from Connection Machine people and anybody else who wants to learn more about this effort. Maybe somebody will participate, contribute. And if you want to get in touch with me, you can email cm@millioncore.com, and I'm happy to talk in more detail. The end.
Thank you so much, Joe. Also no Q&A here. We thank you very much for your presentation and for your ideas. Also thanks for sharing your email address. I hope that there will be some feedback also from here, from the audience. And we now move forward online with the essay film by Max Clausen called Thinking Machines Corporation. It was extra created for the event and for the presentation of the CM here at the ZKM. It will not be screened here. You can watch the film in the entrance hall. It's presented along with the CM there. And we will have now here in the physical space a coffee break till 4:30. At 4:30 we are moving forward. Please be punctual. Also I have to draw your attention to the fact that you are not allowed to take into the hall here your drinks, so please leave everything at the door or in the cafeteria when you're entering the conference again. Thank you. See you in half an hour.
Has your social media feed started to look a little off? The so-called AI slop all over the internet these days. News reports, doorbell camera footage, and more that all look real at first swipe, but have a certain eeriness.
But what's becoming not so funny, how easily reality can be confused with the fakes.
At some point, the world was lifeless. It just was a soup of chemicals.
When I was a little kid, I read H.G. Wells and E.E. Smith and Isaac Asimov. It was great pleasure meeting him and keeping up with him, because how often do you get to meet your gods? I read science fiction more than anything else. I don't read ordinary literature at all. I read some technical things and I read science fiction novels, and nothing surprises me except why doesn't everybody see that this is the right thing and work on it?
I think simple things like people can produce something more complicated and more worthwhile than themselves.
Well, science fiction is like any field. Most of it's bad, but it's full of a dozen people who I think are the great philosophers of our time.
Imagine that I went back 100 years ago and explained to somebody what I did for a living right now. I couldn't tell them I designed computers because they wouldn't know what a computer was. I couldn't say I made integrated circuits and silicon chips because they wouldn't know what that was.
In science fiction, people say, what if something were actually different? And general literature is, what if things were the same again? It's too boring.
I would have to say, well, what I do is I come up with designs which I etch into stone, magic shapes, which fit together in such a way that the stone can be asked questions. And I can tell it what I want, and it tells me the answers to my questions.
What I'm saying is 1,000 years from now, it'll be 1950 when this animal learned to talk.
It sounds like witchcraft, but in fact, that's exactly what I do for a living.
The stuff before was just emotional utterances, because it couldn't describe processes.
It puts us in a different kind of world.
What does AI mean for us as a species? How have we communicated these ideas over literally thousands of years of history, whether it's Prometheus or whether it's the Golem, looking at all these cultural influences and trying to condense them into one object? That's what you can do as an artist. Oh, you're going to MIT, you have to meet Marvin Minsky and you have to meet Danny Hillis. I found out very quickly that although I was in the mechanical engineering department, the AI lab had a lot better parties. So I ended up having my social circle really be largely from the MIT AI lab. There were parties in Marvin Minsky's house where two people were playing on large grand pianos at the same time improvising.
Well, I like to think of the brain as a cloud of resources. The brain has the order of 400 different pieces of machinery, and if you turned them all on, it would be a great traffic jam. So the emotions are selections from this 400 resources. When you're angry, you turn on 30 or 100 of them. When you're thinking about mathematics, you turn on 100 of them, and some of them overlap and some aren't.
Maybe the most important experience I had was meeting Warren McCulloch. And Warren McCulloch was a philosopher and physiologist and great poet. I think maybe 100 years from now he will be seen as one of the great philosophers of the 20th century.
Will we one day in the distant future perhaps even create beings superior to ourselves? Beings who will survive us on this planet? Dr. McCulloch thinks it possible.
Somehow the purpose that a machine, no matter how complicated and how clever, could have, to my mind, isn't equatable. When man has gone, these machines would in essence be purposeless.
I doubt that. I would say in essence they would be purposeful.
And there would be, in your feeling, nothing gone and nothing missing from the world.
Well, you mean in the sense in which the dinosaurs are missing?
No, I mean in the sense of something important.
Well, aren't they important? Weren't they important?
Do you think we'll make a machine to equal the brain, the human mind?
As far as arithmetic is concerned, they're already way ahead of us.
I mean in general, memory, idea formation, a soul, so to speak. When first the machines came out, everybody thought that they did in fact.
I'm sorry, let's leave the soul out.
All right. Well, do you think that the computer will approximate the human mind in all respects?
Computing machines think with a language which is number. Everything else we transfer into number to make them work. Okay? They are lousy when it comes to perception. They don't have any underlying natural language the way we do, that we share with the animals. And when you want to make them spot objects, develop a model of the world around them, you find out they're not the right device. Okay? If you want them to play chess, all right. Our chess playing program at MIT is already a #2 chess player. In another year, I think it'll be a #1. It will not be a master at the end of another year. But it's 6 years old. But in 6 years, it's all from nothing. It's coming up to being a #1. No human being ever did that. So I expect them to go well ahead on these kind of problems because we can reduce these things to number.
but they'll never be able to write a piece of poetry like Warren McCulloch can. Why not?
Not with our loneliness, not with our dream, can earth be taken and our heaven won, but with our toil and ponderous reasoning, and with our little changing of the cosmic stream. Sing then to the men that make the road, and tunnels through the hills and bridges slung, over the wide valley and the deep ravine, till streets are crowded with the whirling cars, and the long leveled track rumbles to the train. Sing to the men that left some safe abode, and gazing fixedly on distant stars, conquered the sea's tumultuous domain. With oar and sail and steam, gallant they clung to their wide quest over unfathomed green, bearing the timorous body in the heart's load, till now through space the wireless word is flung, and the skilled pilot guides the soaring plane. With these we win the world, to these my ode.
And even today, which is 40 years later, sometimes when I'm stuck writing something, for example, I could hear his voice.
I'd read a science fiction book called Have Spacesuit Will Travel by Heinlein. And in that story, the kid wins a spacesuit in the lottery and gets to go to space, and he ends up saving the world and getting the girl, and as a prize for him saving the world, they give him a scholarship to MIT. And I didn't know what MIT was, but I decided that's where I wanted to go. In The Wizard of Oz, it all starts out in black and white, but when she opens the door in the land of Oz, everything turns into Technicolor. That's what MIT was like for me. I saw this whole other dimension to the world. I met all of these people who knew about everything and who were excited about ideas. And the whole world kind of opened up for me.
It needs a good teacher. The teacher comes up to the machine, which contains a vision system for describing things, and I give it an example, for example that, and say, this is an arch. Well, the machine describes it, and the description, the structure that the machine builds up inside its memory is something like this. There are 3 objects found by the vision system. They're all identified as blocks, and it notices certain relations between these objects. For example, that this one supports that, and this one supports that.
What I was really trying to do was meet Marvin Minsky, but every time I would go by his office, he wasn't there. And I started asking where Marvin Minsky was, and they said, oh, he comes in at night and he works down in the basement on this computer that he's building. So I used my key and I came in at night and I went down, and sure enough, there was Marvin sitting there working with some of his students. But I was too awed by Marvin to actually go up and talk to him. So I just hung around and I looked at the diagrams of the computer that he was building, trying to see if I could come up with something clever to say to him. And I noticed that there was actually a bug. There was a design error. And so I thought, oh great, this is my entree to... So I went up to Marvin and I said, excuse me, but I think there's a mistake here. And I pointed out to him, he said, yes, fix it. So I fixed it on the diagram. I said, it needs to be rewired. He said, well, rewire the computer, you know. And so I changed the design of the computer, and then I found another one, and then after a while I stopped asking him. I would just start changing the diagrams and redesigning this computer and rewiring it. And after a while, Marvin just assumed that I worked for him. And so that's how I met Marvin Minsky. And then we would work late at night and there wouldn't be anything to eat, so he'd invite me over to his house. And that's how I met his daughter also. And his daughter became my girlfriend after a while. And I eventually just moved into his house. And we cleared out the basement. And I lived in Marvin's basement while I worked with Marvin on this computer. So by the time I got to MIT, people had sort of given up a bit on this neural intelligence. And they were working mostly on the symbolic intelligence. And the symbolic intelligence is kind of what it feels like to think, because it's the part of intelligence that's very visible to us. And so just as I was arriving at the AI lab, people were beginning to understand that intelligence was kind of more complicated. And Marvin kind of led that effort. And he started thinking of intelligence as a kind of society of little intelligences that interoperated with each other.
Marvin was writing The Society of Mind at that point. It came out, I believe, in '83, which is when Danny started thinking machines. Of course, Danny, as Marvin's PhD student and protege, the Society of Mind was what at least Marvin's students were talking about and thinking about. In our corner of the AI universe, that's how people thought of it. And when the book came out, you know, I did get a copy of the book, and I'm going through and it's like, oh yeah, this is everything that Marvin's been talking about.
What is life? One dissects a body but finds no life inside. What is mind? One dissects a brain but finds no mind therein.
When I was a graduate student, I was very interested in making a thinking machine, an artificial intelligence.
How could solid-seeming brains support such ghostly things as thoughts? This question troubled many thinkers of the past.
There have always been kind of two schools of thought in artificial intelligence. One of them is kind of the emergent intelligent idea. The idea that you'd have some system that was a fundamentally simple system of replicated parts that had in it the inherent ability to organize. So neural networks are the perfect example of that.
To explain the mind, we have to show how minds are built from mindless stuff, from parts that are much smaller and simpler than anything we'd consider smart.
And so that idea was a very early idea in artificial intelligence. And in fact, Marvin worked first on that idea. And he built little electronic neurons out of tubes. The problem with that idea was that it really needed a lot of neurons. And so you had to get up to very, very large numbers before you got that kind of emergence. They definitely had notions of how to do this. They, in practice, couldn't do it very much.
Our first intuitions about computers came from experiences with machines of the 1940s, which contained only thousands of parts. But a human brain contains billions of cells, each complicated by itself and connected to many thousands of others.
I knew that the computers that we had available at the time were not nearly powerful enough to do it. So I had to make a computer that was thousands of times more powerful. So part of why I built the connection machine was to try to get the number of neurons up. And so that's why I started making parallel computers, was to make a thinking machine with them. MIT being what it was, even though I was an undergraduate at first when I started working on this, and eventually a graduate student, I would go to Jerry Sussman or Marvin Minsky or something and say, I want to hire your op student. I would get these great MIT students like Brewster Kahle, for example.
I started working with Danny at MIT early on this project when he was a 24-year-old graduate student. And
how old were you?
I was 20. And I wanted to build the Library of Alexandria version 2. I wanted to build the global brain. And Danny had this idea on how to make a machine that would be fantastic. And I said, oh, how hard could that be? I'm in the very last part of this sort of 60s utopian generation. He wanted to build a machine that would be proud of him, which I thought was really an interesting way of viewing the whole thing.
We just had the ability to start making chips ourselves. I figured out you could actually make like 64 very simple computers on a single chip.
Parallel processing at that time meant 2 processors, both very powerful, maybe 4. And above that, it's just too complicated. You can't do it.
So I started designing chips like that and imagining big arrays of these, that you could have 1 million of these was my initial thought. Later I scaled it back down to 64,000 out of practicality. But the original idea was you could have 1 million computers and they would all have the ability to talk with each other, and you could use them like neurons, and you could use the kind of McCulloch-Pitts learning algorithms.
I was an undergraduate at MIT. I could design chips. I mean, what the heck?
The project started getting more and more expensive, and it became a little bit ridiculous having a student have all these people working for him and spending millions of dollars. And so eventually I realized I had to start a company on the outside to do it. So that's how thinking machines got started.
Especially then in the early 80s, it was unusual for a doctoral candidate to start a startup company and actually get millions of dollars to carry out the idea. But because he was a protege of Marvin Minsky and MIT has kind of good connections,
ultra-fast computer so powerful, it's revolutionizing work in laboratories and businesses.
Really, as a 24-year-old Danny's kind of wacko dream. Yes, there's Marvin Minsky, who seemed more establishment, or at least older, but it was still kind of wacko. Let's give this thing a shot.
It turned into the largest employer in Cambridge, actually. It had about 750, 800 people.
Many scientists thought such computers couldn't be built for decades, but as David Barron reports, the advanced technology is proving itself today.
These are the heady days of AI and computers when we could see the future.
You know, he had, I think, 150,000 square feet of prime office space around Kendall Square.
Hillis's multi-million-dollar machines and those built by a handful of competitors are based on a technology called massive parallelism.
How do you go and make a company out of a bunch of bonzos from MIT and make that come about and communicate?
Danny Hillis is a legend in the world of computing.
It really turned into a company, which was not really what I had intended exactly. I hadn't really thought that part out so much. I just wanted the machine.
What a fantastic trip.
Hello again, and warmly welcome. I hope you have new energy after the break. And we start now with a lecture by Heiner Igel. I'm happy to introduce Heiner. He is professor for seismology at Ludwig-Maximilians University in Munich. He studied geophysics in Karlsruhe and Edinburgh and received his doctorate in Paris, developing parallel modeling tools for seismic wave propagation on the connection machines, CM2 and CM5. He later worked in Cambridge and now focuses on full waveform inversion, high-performance computing, and rotational ground motions. He is a member of Leopoldina and a fellow of the American Geophysical Union. Please welcome Heiner and enjoy the presentation.
Thank you very much. Welcome everybody. And I told Tamiko in the coffee break that I'm so speechless from what I heard so far that I may have a hard time finding words. So anyway, let me change gear a little bit. I'm a user of the connection machine and have been in the early 90s. But before I start, a very personal comment. As Daria said, I studied here in Karlsruhe, and I was actually, just before I moved to Paris, I was living 250 meters away from here. And sometimes I would come probably right here, or maybe a couple of meters away, playing the oboe. Why? Because this was a ruin, a total ruin. And my oboe playing was so bad that my people I lived with, they said, you know, maybe just go over there, but it was also a great sound. So I entered the fence, which was totally forbidden, and just stood really honestly a couple of meters away from here. So anyway, I'm moved to stand here now with this beautiful framework. So I have a co-author. This is Peter Mora. Some of you know him. He worked for Thinking Machines at the time, and I will tell you a lot about his and the reason why this connection machine came to Munich. So before I start, let me introduce and motivate a little bit my area of science. So it's already kind of a little bit made visual in this graph. That's of course a recent graph. This is a globe, and through the oceans we look into a tetrahedral grid of the Earth. So whatever we do, I'm a seismologist, we're interested in understanding the motions, the vibrations of our planet. Our planet is constantly in motion, not only when there are earthquakes. So one of the key things, and that hasn't been mentioned yet, everything we do, if we simulate physical system, we discretize our domain. And our physical domain here, it could be the sky, but here it's the Earth. And we solve partial differential equations on it, in this case, the wave equation. And if we zoom in a little bit, this is actually a recent simulation of an earthquake in the L'Aquila earthquake in Italy in 2009. You see this wave motion. This is a wave field after a certain time. You see it's relatively short wavelength. And that already tells you, if I want to discretize these wavelengths with an appropriate number of points in a 3D medium, this is goddamn expensive. And it has been expensive, at 36 years ago when we started, and it still is a very expensive endeavor today. Now, what we do is we solve a data fitting problem. That's a very classic. That's what many people do in natural sciences. In our case, this works like the following. I mean, we have an earthquake here. Again, this yellow star is the origin, the epicenter of that earthquake. And it's observed. We observe ground motion. These are these wiggly line seismograms at these triangles. And actually one of those is BFO, the Black Forest Observatory, which is run by KIT here in the Black Forest. And we record these ground motions, which is the black lines. It's an up and down motion. And now what we do actually, since basically those times starting with the connection machine, is we try to fit the complete waveform. So we simulate the wave equation with an Earth model, and we get these red lines, and we try to fit the observations. Sometimes if you look down here, bottom right, MAT, or here, it looks actually quite good. And sometimes here at ESK, this is in Scotland, or even at the Black Forest, it doesn't look good at all. So what happens is you change the model, you change it in an iterative way, using adjoint formula or Monte Carlo type methods until you find a model that fits the data. So this is an inverse problem or data fitting, and it's similar what's being done when you go into MRT or a CT in medical tomography. So we call it seismic tomography. If that works well, you end up on a global scale with something like this. Again, this is recent. This could not have been done 40 years ago. You see this is a tomographic image of the Earth's interior with red blobs where it's actually slow or hot, or blue blobs where it's actually faster and colder. And this is the way we understand the workings, the dynamics of our planet in the context of plate tectonics. I could spend a long time talking about this. That's not the topic today. So let's, well, yeah, okay. Okay. So let's go 36 years back. Actually, really more or less exactly on the day 36 years ago, I went to Paris to work at maybe the most, you can arguably the most ugly building in Paris, in central Paris. This is Jussieu. It was actually built in the 60s to protect from students, so it's almost like it has, you're laughing, but it's true. It's like protected like a castle. And so we were sitting in Tour 24. This is 24 here. And I many times, also Peter Mora, I talked by Zoom to him this week on Tuesday, and he talked about this excitement working in thinking machines. And the same was true here in Paris, because we were sitting, you can't see here is the windows. When you were entering that matrix of buildings at like 1 o'clock at night, there was one office was lightened, and that was our office, where people were working with the connection machine. The connection machine was put in the subsurface underground. There was a glass, and so it was accessible. Unfortunately, this is at the time we didn't make photos, but really this arrangement was there, and we had an inauguration, and the bottles of champagne were put on this. It's a perfect bar, and I wish there was a data vault somewhere. And as you said, you know, this was 20 gigabytes of memory. And I like to also tell that to students, it's similar to what you do. So that was the context. By the way, it's not a problem if you work inside this really ugly building in the middle of Paris, because if you work very late, you could go out and have dinner or lunch at midnight in the Quartier Latin here next door. So it was a really great place to be. So this is probably the slide. I will get carried away talking how we got there. So this is Peter Mora and Albert Tarantola. So maybe Albert Tarantola was an incredibly charismatic mathematician who moved to geophysics because he said they are on the 4th floor, because he was on the ground floor, and they travel a lot. So he started working for geophysics, and he introduced and pioneered basically the adoption of Bayesian probabilistic methods for inverse problems in the mid-80s. And Peter Mora was a Stanford graduate. Here comes Stanford. And he gave a talk in 1986 at the Society of Exploration Geophysicists. And after his talk, somebody from Thinking Machines approached him and said, "Don't you want to come and consult for us?" And eventually that happened. Peter consulted as a PhD student for the simulation part, and he said, "This is the first time I had some money and I could go to a restaurant because they were paying me so well." And he talked about his excitement, talked about how Richard Feynman looked at this wave propagation problem, said, "This is amazing what you do here," and wanted to understand what's happening. And so I actually wanted to work with Albert Tarantola because I was fascinated by this concept of using probability to understand in the most honest way the value of data on a certain problem. And I make a statement here. I think if we lame people would be able to deal with with probability and information in a real nice way, we would not be in a world like we are today. So I wanted to learn about this. But then in '89, actually, there was a meeting in Berlin just a few weeks before the end of the Cold War, or at least in Germany, the wall came down. Peter Mora showed me this picture. And that was it's actually a cutout of a sphere inside a 3D cube of global wave propagation. Way too long period, too low frequency. But he got me excited about also the visual aspect of this. It was just beautiful to see these waves. So when I started in Paris, basically I first started to work on that forward problem, which is the simulation of seismic waves. So how did the CM got to Paris? At the time, the head of the institute, the chef, Institute of Physics of the Earth's Interior, was Claude Allègre, a famous geochemist, socialist, good friend of Lionel Jospin, who actually died on Tuesday. When Peter Mora told me about him, and because of that direct connection, they very quickly got money to get this machine to IPG. But it was really the vision of these two guys who they understood this is very, very important. And I should also note that the research group there was funded by all the oil companies because they were interested in this wave propagation, imaging as a fast way of knowing should I drill here or there. Okay, so we used it for other things, but this is how it got funded. So quickly on our physics problem, it's the physics of waves in the Earth is almost the same as the physics of a vibrating string. And just to make a point here, if this is like a displacement field, we need partial derivatives. So we need to calculate a finite difference. So at the time, we used the finite difference approximation, which means, well, you need the slope of this function here, and you get it by taking information from points aside. So to make it simple, each point here would live in a different processor. And so this is called near neighbor communication. And at the time, it was communicated that this near neighbor communication is what is really optimized and really fast on the connection machine. You talked about convolution. A convolution is a global communication, which is more difficult, but this was really near neighbor communication. And if like the bottom line here would be the discrete version of the string, and the way simulations work is we extrapolate in time. So at some point we would like to calculate the state of this point, and we use these gray points here, and those are all sitting in the next neighbor. So this was extremely fast, and those were these early finite difference solutions to the wave equation. So to do that on the computer, we use the so-called circular shift routine, which the application engineers told us this is one of the most optimized functions you should use to do that. So the way this works is a vector A, 1, 2, 3, 4, 5, 6, 7. And if you shift along this dimension one by one element, you end up a circular shift. The last one goes in the front. And this is how we consider that as a convolutional operator. Here's the word convolution again. And here's the connection machine Fortran directive with which we did something like that. This is for the specialists. So some examples, a gallery, what we did. This was, to make these oil companies happy. This was my thesis, is fitting things from data from the Gulf of Mexico. Here's a ship that pulls a geophone string, receiver string behind it, and there's explosions, and you get vibrations that you record to find oil or gas in the Gulf of Mexico. And here's an example, and I deliberately show that because at the time we couldn't just do a screen dump. We were taking photos in front of the screen and afterwards develop them, and then you realize, oh my God, the lighting was completely bad, and so it's all foutu. It's gone. But those were the days. Waves in subduction zone, and something I'm a little proud of is that this is, I think, then later on the CM5 or CM200, those are the first snapshots of global wave propagation, quite realistic inside the Earth. And this is really a realistic wave field. This is how the waves are reflected by the, this is S waves, shear waves, by the liquid outer core. And people's jaw was going down when they saw this at the time. It was really, it's not necessary of a high scientific value to know these snapshots, but it's just really beautiful, and you can develop intuition what happens in a physical system. So it's really, really cool. So I was really glad to see that picture that somebody showed of you with a pizza, because you guys developed that machine to do AI, and so this is what AI does today. If I tell him, give me a computer nerd, and here's the pizza, okay? So here we go. So I gave my my talk the title "Joy of Programming." Why joy? And now this is an important point that hasn't been made. Coding the CM was incredibly simple. It was a high-level connection with Fortran or others. It was a high-level programming. I'm a domain scientist. And by the way, I was the last one to get into programming. I studied geophysics to work outside and travel the world, not to become a programmer. And I told my supervisor on Tuesday, did you know that after half a year I almost dropped out? He said, no, I didn't know. Honestly, everybody else was programming much better, and I felt really bad, but at some point I got really excited. But this is the point. There were these directives, they were simple. There was an implicit parallelization. If you said if you defined an array, a 3D array, said A equals 0, it said, oh, I'm not addressing a single point, so it has to live everywhere. Wow. And at some point there was a visual debugger. I can't find anything on the internet. It was revolutionary. You had a picture of your field. You could click on a value, on a point, and you got the value. Wow, that was amazing for a debugger. I get goosebumps when I talk about it. And honestly, and we had application engineers. And all those people who share with me that story, I tell them it went downhill ever since. What I mean downhill ever since means, and somebody said this already in the presentation, you know, in message passing, then the computers were nodes of shared memory models. You had to parallelize on 2 levels, like with message passing and OpenMP. And for domain scientists, it became very, very much, you know, an order of magnitude more complicated. So I think, and that's the point of my talk, we had a very small time window of a couple of years with paradise conditions for simulating at least domain decomposition-based simulation tools in physics. And it was really amazing. And that's, you know, the going down is what I gave up basically in 2000 and went to MPI. Before we tried high performance Fortran, actually with a DEC company, but it was a failure. And anyway, here we go. So to finish up, in 1989, the CM won the Gordon Bell Prize for the fastest machine per buck, per computation. And just on a side note, if you look at we used to discretize the world in blocks like you see here on the ground. I really like this, and that's not good for complicated geometries. So I pushed, starting from mid-90s, to develop methods for unstructured grids. And so in the end, we used the discontinuous Galerkin method which was started 20 years ago, immediately with the people from the computational science. And I may say that I have not coded one line of code, but it's my assistant who represents that code now, won the Gordon Bell Prize, or part of the team that won the Gordon Bell Prize last year. And at least she would not have come here without me starting in basically growing up with the CM legacy. And again, to be there, to arrive in Paris 3 weeks before the Connection Machine 2 was delivered is just, one of the lucks of my life. So finally, a few years ago, I realized there's a musical equivalent to the C-shift routine. So there's, if you take this rhythmic pattern here, actually two of them, you can represent it as a binary vector if you want, and if one is shifted, like a C shift, it's actually with a -1. And these two lines are played at the same time. You get a very interesting pattern, and that's actually what one of my favorite composers, Steve Reich, has composed in the 1960s. It's called clapping music, and you will hear this in a short moment. So to finish up, again, it's really what I mean. It's gratitude. What a coincidence that I went as a really I was not interested in programming, but I got there. This machine was there. And it's one of the lucks of my life, and it has been transformative. Like in many other things, this is the first time. Domain decomposition, still here today. Everybody's doing domain decomposition. It was there at the first time. I think it was a paradise to program at the time. And thank you, Thinking Machines, for the receptions. New Orleans, 1992. I'm not sure who was there. There's a drilling rig in the harbor. This was a Society of Exploration Geophysics. So we all went there as students, of course. We went to many receptions, but Thinking Machines was amazing. So they had this seafood and jazz music, and this oil rig was lifting slowly over the next couple of hours, 50, 60 meters above New Orleans. Anyway, it's absolutely amazing. And of course, thanks to all of you for the most beautiful machine ever. Thanks very much.
Wow, thank you so much. I think it was world-class clapping music. And I need to mention that it was performed by Tibor Kate, Xin Luwei, Finn Kiefel, Tolga Anla, Minoru Saito, and Sean Xiao from the University of Music Karlsruhe, class of Vanessa Porter. And also thank you so much, Maria Stange, I don't see you, but you're here, for communication and for arranging this. So now I would like to draw your attention again to this live translation app. I think it was not working in the morning, I got the feedback, but I am sure it's working now. Auf Deutsch. Bitte nutzen Sie die Übersetzungs-App, Live-Übersetzungs-App, wenn Sie sich nicht so wohl im Englischen fühlen. Sie können den QR-Code einscannen und live die Talks verfolgen. Genau, die sind auch hier im Raum hinten verteilt, wenn Sie jetzt keine Zeit hatten, das einzuscannen. Now we move forward with our next speaker. It's Thomas Lippert, and he is director of the Jülich Supercomputer Center at Forschungszentrum Jülich and professor of modular supercomputing and quantum computing at Goethe Institute Frankfurt. Welcome. Thomas Lippert has led major initiatives in high-performance computing, including the Helmholtz program Engineering Digital Futures, and contributed to European efforts such as PRAISE and Euro HPC. Since 2014, he has been instrumental in developing AI capabilities at Forschungszentrum Jülich, including the installation of the supercomputer Jurals and exascale computer Jupiter. So please give Thomas a warm welcome, and he will share with us some reflections on from connection machine to exascale.
Thank you so much for this very nice introduction. I have to allow something here. Okay. Yeah. Okay. Let me see. Start. I hope it works. Keyboard setup, I don't want that. It needs to set up. Great, okay. Good. Yep, very good.
Let me try this. Okay.
Yeah, it works. Thank you so much. When I start, I would like to ask you a short question. So what do you think, how many connection machines, beautiful machines, you would need to get the performance of a big modern exascale computer? What is your guess?
1 million.
One?
1 million.
1 million. 1 million is the first guess. Second one. And more guesses? 100,000? We'll see. Okay, thanks for these three guesses how many connection machines you would need. In fact, one of the answers was correct. I tell you at the end. Okay. So when I came to Wuppertal, when I came to Wuppertal University, this was in 1988. There was not yet a connection machine, but there was a spirit of computing which was very interesting for me to join the group of Professor Klaus Schilling at this time in the field of lattice quantum chromodynamics. So actually, I was before a little bit reluctant to use computers. I was working in supersymmetry and a little bit in string theory. And at this time, I used to write my equations on very long pieces of paper, because they were so long that you needed nearly 2 meters to get them, so to say, solved. Later I learned that you can do much easier, and especially this machine that you see in front of you here was very instrumental for that. And I thank you very much, Tamiko, for bringing me to this place today, inviting me to talk and to try to convey to you how I was, let's say, more or less motivated to enter the field, and finally also to build or to design at least computers that were the successors of these original ideas in parallel computing. So the word parallel will be a very important one, and of course the question of how those parallel computers are programmed, software, and of course some of the results will be shown to you. So this was in 1990, and it was a big connection machine CM2, and in 1990 also Klaus Schilling, who was my PhD advisor at this time and became a real friend to me during this time and later, and he is here today. Klaus, maybe you get up so that everybody can see you. He was the one to bring the connection machine CM2 to Wuppertal at this time, and this was the start of a long journey for many people who then learned to program in parallel and to understand computational science in depth. So we had a big pleasure that at the inauguration, the Landesvater, this was Minister President Rau, came, and on the right side you see again Klaus, a little bit younger, and he asked very sensible and reasonable questions on this technology, and actually he was also one in Germany who was instrumental to bring universities to our country, to bring education and real university knowledge to Germany. And so he also was coming to our place for the inauguration of the connection machine CM2 at Wuppertal University. Of course, this machine was a little bit smaller than the big one. It was a university machine, so it was about 1 gigaflops, billion operations per second, while I think the big one was 8 at this time. And it was installed in a new institute for applied informatics. You see, it had 8,192 one-bit processors. Actually, finally, the machine was equipped with Vitek processors, floating point units that could perform floating point operations much faster, of course. But the spirit of this machine to be connected in the way that it operated, the one-bit processors, was still there and has influenced our thinking very much. So what was the purpose of having such a machine primarily in the group of Klaus Schilling? This was to understand the forces between the quarks that build up the nucleons, the proton, mesons, etc. And the forces are mediated by so-called gluons. And actually, numerically, this leads to, so you see, this was a scripting of the talks we gave at this time. This was on transparent sheets. You see a matrix M, and you see vectors. One seems to be unknown, so it's called X. The other one is the source vector. So that's very familiar to many people in the diversity of fields. The only problem is that this matrix looks extremely ugly. So it has, I think, a lot of indices, at least 3 indices. And so you have the spin index and you have the color index. So that's called quantum chromodynamics for the color. And you have the spatial index, so it's on a lattice. And it is not just a simple 3-dimensional lattice, it's a 4-dimensional lattice. And it's even more complicated because it's not a Minkowski space, it's a Euclidean space, and you have a transformation between Minkowski and Euclidean space. All of this you have to learn as student, and on top you have to learn how to program in parallel. So this was quite exciting this time at Wuppertal University. So this was our task, to include fermions that amount to this matrix M into the computation of lattice quantum chromodynamics. And this required a lot of knowledge, and one guy, and I especially mention him here because he comes originally from Karlsruhe University. This was Andreas Frommer, joined as a young professor very early the Wuppertal group, and with him and Professor Schilling's drive and the connection machine, one could do quite something. So the first real important element was to introduce an algorithm that was invented in Utrecht. the BiCG step. And the BiCG step turned out to be most important because it gave a significant speed up over well-known algorithms at this time. And this was quite some breakthrough, made immediately the machine well-known at a place, and people were very much quoting and citing our results at this time. So it was adopted, this algorithm was adopted, and I can safely say that without the connection machine, we would have not made any impact here. So, as I said, not possible without the CM2. And in 1992, we then had a very interesting workshop with quite a diversity of topics. I can just zoom in a bit so you see what's going on at this time. So it was on computer graphics, it was convolution problems, large-scale structure of the universe, computer science stuff, raycast algorithms, etc., that were all transformed, ported on this machine. This means this machine was a universal parallel computer. I would say the first one that was available worldwide and could be used as a universal machine. So Klaus gave this talk, I gave this talk, but what is more important even here was that at this time also already artificial intelligence algorithms have been ported on this machine or even developed on this machine. So this was in the field of experimental particle physics, elementary particle physics, by Professor Bex from Wuppertal, and you see on the down side of this page, you see, let me find out, the word connection machine model CM2. That was used to reconstruct traces automatically from the Delphi experiment at CERN at this time. So this was more or less the first time I heard about using a parallel computer with artificial intelligence in this field. So, but this was not the only purpose of the machine. It was also a university machine, and it was used for teaching. So there was a quite known new sort of exercise group, which was called the Wuppertal Computer Theoreticum. And in the Theoreticum, a lot of fields have been, let's say, treated. So it was for the, so again, you see, this was my first attempt to use a plotter to get transparency written by computer. So this was probably 1990. And you see what we did. We were implementing a lot of former programs in parallel on the connection machine. So this was, of course, new land for us. Klaus Schilling had initiated that, but the most important thing was that there was already a software stack. Yeah? Everything that you needed to do proper computational science, wait a second, was on this machine available. So you had programming languages like C*, Lisp, and of course we use CM Fortran, and I can only confirm what I heard before. The CM Fortran programming language was just like writing an analytical formula. It was not far from that. So if you had an idea, you wanted to realize, of course you had to think of the C-shift, and the C-shift was a circular one. Of course, when you did not have a circular shift to perform, you could just omit, so to say, the shifted one. And it was not the only thing. There was scientific libraries, graphical libraries, Crystal, where you could look into your code, and you had this extensive matrix vector type of library, which was a breakthrough for us, eigenvalue solvers, random number generators, and so on and so on. All there to do proper computational science at a very early stage of this machine. Yeah, that was how we started into teaching, and what we did was a lot of problems. And as you can see here with these sketches, this machine very well could map codes or we could very well map our codes onto this machine if they were regular, if we could perform C-shifts, but we were also able to do some more complicated layouts, as you can see here. And so we had, I think, 6 or 7 different larger projects. Already at an early stage later we had about 15 when we evolved it. And these were half years, 1 semester projects for the students. And these 1 semester projects were extremely attractive. So I think all over in the time when I was in Wuppertal, more than 60 or 70 people did that. And a lot of them you can find today in computational science or in related fields in Germany. We also had an application engineer, an on-site engineer. This was at this time a friend of mine and is a friend until today. It's Terry Donche. Maybe, who knows Terry Donche? Many of you, of course, know him. And Terry was extremely helpful for us. Without him, the uptake of the machine would have been much more difficult and much more slower than it had been finally. So that was quite an important asset that thinking machines put out on-site engineers at these important sites, and of course we must have been an important one, otherwise we would not have had an on-site engineer. So this was also the time when things changed, and you might remember in 1993 there was the top 1 machine in the world, the CM5 1024, with 130 gigaflops nominal performance. So this was a real breakthrough, because for the first time such a big parallel computer made it to this position of the list. And of course Klaus and people in Wuppertal wanted to have also a smaller one. So we got a smaller one. It was called CM5 and later CM5E with 4 gigaflops and 10 gigaflops, quite something at this time, factor 10 more performant than the CM2, but also with 64-bit processors, so for computational science fulfilling this important requirement. Yeah, but it also made a change in using a preferred programming language. Of course, you still could do it in CM Fortran, but MPI became more and more important. And I have made a table here you do not need to reach, but you can be sure that from left to right, things go down like this, as we have seen before. So I believe the progress of computational science was very much hampered by the fact that MPI was introduced. Of course, it was more flexible, but it took us years to take it up, and it took us much of the time for to teach students and beginners how to do MPI. While if you do CM Fortran, after the first day, people can program. So that was really an important message to understand, that the CM, the connection machine, was much ahead of its time. But of course, the other big companies wanted to introduce a language that was much more profitable for them. And there was also the question of legacy codes. What was easier what language was better to use to transform to port all the legacy codes? This, I think, has not been yet decided, but I believe it would have been easier with CM Fortran. Yeah. So there was also another message to learn. If you understood parallelization, you could use parallel constructs to do things better. And here is one, at least, where I believe this is so. It is a parallel SSOR preconditioner, which was more effective if you had more parallelism. So that's an interesting thing, and with some tricks for our type of operator, one could get to large improvements. So already with the one before, we are at a factor of 6 to 8 of improvement just by algorithmics alone, and especially also using parallelization as even a means to improve, not only just to have the parallelization speed up that we get. This was a crew at this time, and you see again Klaus, the left one is Andreas Frommer. I should also mention Per Überholz, who was a very important person at Wuppertal University at this time to get the machines running. This is me, looking a little bit younger, and on the right-hand side you have Norbert Eicker, who is also professor today at Wuppertal University and one of the experts of parallel computing at Jülich Supercomputing Center. So in 2000, and I now go through the machines a little bit, we had learned a lot how to program, how machines are built. We dared to build an own cluster computer. And here it's important to understand we did it not just by ourselves. We had made some failed attempts before to connect processors. We did it our own, we used Ethernet, we used 10 megabit, 100 megabit Ethernet. It all did not work because the real cluster-aware operating system was missing. But there was one cluster-aware operating system that was developed here in Karlsruhe by Professor Walter Tisch's group and himself. He came from Stanford, where he had very much contact to the people around Sun, but he decided not to join them. I don't know why. But later he came to Karlsruhe, and he had built a hardware here, a parallel computer in 1994. And for this he also had developed an operating system, which is a peer-to-peer type of daemon system on the machine. It's self-aware. So it comes closer, ever closer to a machine that knows things about itself. And it's called Parastation. And with Parastation we were able to operate a system with 2000 alpha nodes, quite fast one, alpha DS10 processors. So these were one processor nodes and could reach 100 gigaflops. Now we have a factor of 10 more than in 1994. We have a factor of 100 more than in 1990. But of course this was not the fastest parallel computer at this time in the world. There were some that already had reached teraflops. So gigaflop, teraflop, this was the first step in 1 decade. And so here you can see, why do I show this to you? You can see Walter Tischi named here. He was one of the speakers when it was inaugurated because it was his technology that allowed to run this machine. In 2000 also we made a crucial step, published a book on numerical methods in lattice quantum chromodynamics, and I can really say without the two connection machines, the three, CM2, CM5, CM5E, such progress would not have been possible. Then we proceeded and had already in 1992 a 2 teraflop system. This was built by a successor of Klaus, Zoltan Fodor, who is also a very, let's say, successful scientist in lattice field theory, but lattice field theory requires big machines, so he also built his machine, but we now have reached teraflops. And so it went on. We had then, by all this knowledge and this competence with all the people together, the chance to get a special research focus, a Sonderforschungsbereich, TRR 55, by the DFG, very much based on computer simulation and on machines. And one part of this of this Sonderforschungsbereich was to build a machine. This was a QPACE system, which was then built in 2009. It was a world record supercomputer as to energy efficiency. It was #1 in the Green 500 list, and it had a self-designed network, and it already had reached 50 teraflops. So the spirit of 1990 was carried on at least until 2009. Let's see if this continues. You see it. Here's the small certificate. In 2000, here I did forget to put in a picture in 2010, so it's a white space, but then you can imagine anything you want, but I can tell you what it is. It is the Eugene machine at Jülich Research Center, at the Jülich Supercomputing Center. This was the first petaflop machine in Europe we brought there. Again, a machine that was very much based on the original spirit of the connection machine, and the successor of it was UQueen with 6 petaflops in 2012. a long-time workhorse for computational science. I think Heiner also was working on it, I guess, probably. And it was working until 2017 or 18 at our place. So UQueen was also ahead of its time. It was interesting in a machine that could scale up extremely far, but it was a little bit weak in doing smaller jobs. And as you know, you always have a partition, a sort of partitioning of the system and a real portfolio of different job sizes. And you try to get it in. Sometimes you have very big ones, sometimes you have a lot of small ones. And the machine should be equally efficient and effective for all of them. This was quite a problem, and we had to tackle this problem, and we tackled it. But before we did that, in 2015, I would like to mention that a very interesting result could be achieved with all these machines and reaching back to the first simulations with dynamical fermions. Then this technology had far evolved, and one could, with all the algorithmic improvement now, through multi-grid algorithms, reach physical quark masses. This means that the condition of the matrix, which was extremely bad at the physical quark mass, could be overcome by algorithmic means. It had a real impact on generating these ensembles, and for the first time, the proton-neutron mass difference could be computed. So we are very proud of that as a physical result. This is a textbook result. It will stay with us forever. In 2020, the multi-grid could really start to pay off because we had a machine with 4,000 A100 GPUs. This was one of its big advantages. It had a lot of degrees to parallelize. And you know, with multi-grid, the bigger the system, the better it works. At least it should, in theory. But there is another line, the last one here. This is the question how well this machine performed with AI. It was conceived not to do only simulation, but also to go for the first time to large-scale AI models. We had pursued the AI activity since 2012, and this was one also of our ideas to base the future technologies on GPUs. In 2015 we decided that. So in 2020 we had the second of those machines that were equipped with a large number of GPUs. These were the A100 GPUs, and I can say it was the first large AI trainer in Europe. And just today I received a call by the ministry in Germany asking us, please continue to operate the machine, because it has such a very good, let's say, AI performance and allows still to train large models. But then we started out for the next round of systems, and so we planned in 2020 already to go further, and in 2024 we have had the pleasure to build this concrete plate. It's about 85 meters times 45 meters. Looks a little bit smaller here, but it is huge if you go there. And we decided that the next machine should be built in containers. So the idea of machines with boards or with racks or in smaller compartments like the connection machine has evolved to containers. You fit together all the racks and all the stuff at the factory. You let a big truck come and you bring the containers on site. And this was when Jupiter was assembled on this concrete plate. So you had 300-ton cranes to bring those parts together, altogether about 50 containers, which then are joined, and you can remove the walls in between, etc. Now you see it as it is today, and this machine now can, in some sense, really trace back to the early efforts with the connection machine. Much of the spirit, much of the technology, much of the software stack still has evolved from that. Of course, now the idea that you have one processor. This is actually what the connection machine was. It was composed of a lot of little small processors, but finally it was one big thing working on one problem. So in some sense, one processor. This idea has continued with this machine, and it has many more processors. If you look at the roof, you see this because you have to cool all of these processors, but you see a repetitive structure. And so this is the way how we handle that. We know we could just enlarge the machine to the next step. From the inside you see that, so it's really one big element in a container, and of those we have 7 large containers. It is a modular supercomputing architecture in the sense that you have one network, again a little bit the spirit of the connection machine. This is actually a network that's composed of different topologies, but that works together. You can go from one part to the other. On the upper side, on the upper row, you see the storage systems. You have 3 storage elements. One is a fast one in the middle with SSDs, and you have spinning disks, and we have tapes altogether more than, I guess, 1.5 exabyte in storage compared to 20 gigabyte of the data vault. And then there is a modular composition of systems. There is what we call the booster, that's the exaflop GPU engine. There is a cluster which uses CPU. CPUs are still important elements, but they work together. So this is a virtual system, and it will be complemented by a third one, which is an inference engine for AI, and in the future also by quantum modules, which we already have at our place. We have 7 quantum computers. 2 of them will be connected to this machine. Why? We want to connect them because we believe that we can, at least for a part of our problems, beat Amdahl's law with that, at least alleviate the implication of Amdahl's and Gustafson's law. This is one theme that goes with me since more than 30 years. I feel that these modular architectures open up the way to beat Amdahl's law and to allow for progress. So assuming that you would have one of those processors or one of those modules in a 100 gigahertz or terahertz range, you immediately know that the speed up would be incredible in the, let's say, theoretical application of Amdahl's law. So that's the idea, to go forward and not just to have a computer, but to have a computer that allows you to think how the next computer can look like. That's what we do at this place. So you see, this is a booster. You take out those parts of Jupiter that make up the booster, and so we have 7 double containers, 125 racks, 20 racks per double container, 6,000 nodes with 4 NVIDIA Grace Hopper superchips per node. And of course we balance it by the right network interface, which is again 4 NDRs, Mellanox NVIDIA NDRs, and so on. And these numbers for the tape and for the HDD are already dated out. Outdated, they are actually larger. For the impact, we had 17 megawatt measured. For the exaflop, for the steady operation, it's about 12 megawatt. It's not as much as people thought in the past. Yeah? So there's really some progress. This is a booster. As I said, it's 24,000 of those chips with NVIDIA. Without NVIDIA, one could not do this. I doubt that the effectiveness and the AI speed can be reached with another technology. So, and the cluster will join this with a European processor by SciPearl very soon. That's the next element. It's much smaller, of course. It should not scale to exascale. As well as the inference module, guess which elements will be in. I cannot tell you, but you might already know what one can use for inference of AI models. Now, going to the interconnect, just to make this comparison again, this looks a little bit more like a brain. This is actually the number of endpoints of the network of Jupiter. These are 36,000 at least, will become more. And of course, no one of those points should fail. So this is just some high complexity, requires a huge resilience of the system. And there's also some first results. There was the first global simulation of the full Earth system at a very small grid spacing of 1.25 kilometers. This year's Gordon Bell Prize, so we also have last year's Gordon Bell Prize. We also have a Gordon Bell Prize in climate on this machine. This is not, and it was not the full number of GH200 because the topology of the code did not fit all of them. But in future we will be able to do so. The same here, a record-breaking quantum computer emulation, so a real exact emulation of quantum of the spins, for the idealized spins, of course. You can also do physical embedding, but here, if you do the ideal one, you can go up to 50 qubits on 16,000 GH200. Here you need a power of 2 to do that. And to use the CPUs and the GPU simultaneously, also the memory, you have to use simultaneously, and it's quite some achievement over 48 qubits. It always goes with a power of 2 here, but it also tells you that the Japanese with their K computer had really a big and good machine in the past. So, yes, this is the last one. Now I can answer the question. There was a winner. It is 10 to the 9 connection machines. It means that a 1 gigaflops machine with 1 billion operations can be composed today into a machine that can do 1 billion times of this performance. I think this is a great achievement of computational science, but you have to start somewhere. And the start was a connection machine, at least for me. Without that, I would not be in the field. Thank you very much. So. Careful.
Yeah, thanks a lot.
Q&A now. Yeah. Okay. Fine.
For that very interesting talk. Yeah. Also, give us the timeline, the historic timeline from the past now to the very present, actually. And of course, one question for me as a computer scientist is, where are the limits? I mean, the Jülich supercomputer is now very big. We've seen the construction, not as small as the CM2 that stands here.
And not as beautiful.
But also very complex. So yes. What do you think? Do we run at limits then in terms of energy, in terms of complexity? And we often talked about programmability. Yeah.
So I think in terms of programmability, we have made a lot of progress. Yeah, so we had, of course, this transition from the pure data parallel languages to a language like MPI. And this was a problem for us, for all of us. And it was also explained before. Those people who were used to the CM Fortran were really disappointed that they had finally to go to MPI, which reduced their productivity by factors. Now, I think this is more and more overcome. Still, we do not have such a beautiful debugger as Prism has been. Yeah? We don't have it yet today. We have made huge efforts to get performance analyzers, etc., built, like Scalaska in Europe and so on, but we have not really achieved something that was similar and allowed us to look into the machine step by step like a microscope. Yeah? So this was not yet achieved, but we have made a lot of progress. The real problem will not be there. The problem is that at a certain stage, in order to get more performance, and you know the more performance you need to overcome the exponential problem that you encounter if you want to go one step in any problem that is three-dimensional, has a lot of modalities and resolution. Even if you want to go a factor of 2 in all dimensions, you have already a factor of 1,000, 2 to the 10 in efforts that you have to put in. So this means you go from petaflops to exaflops, yeah, for a factor of 2 in all dimensions. So this we would want to increase to go on. But I doubt that it will be with present technology. I believe the next step will be cryotechnology. So we have to go to a computing, let's say, situation where you do need much less energy, where each of your switching steps goes down by in energy consumption by a factor 1,000, 10,000, 100,000, which is the case for superconducting transistors. And here is a lot of efforts are now coming up worldwide. In Europe, they are a little bit late again, yeah, as usual. But this will be at least one part of the future. Many people say photonics computing. I would not exclude it. What I believe, the photonics will play a big role in the communication. Yeah? So this development is very good. But in computation, you would not want to lose the advantages of all the chip technologies that we have developed. Yeah? How to program them. RISC-V is one of those very important developments. And if you can transfer it to such type of processors, you will fit a Zeta-scale machine in a small box. That's what will come if this goes on like that. The question is, if you fit the data into the small box, do you get the photonic communication as effective that it goes into this small box fast enough to feed your compute engine that you have? This, in my opinion, this will be the future.
By photonics, do you mean photonic quantum computers, or I don't know? Are there other just regular computers that also use photonics?
I also mean that there will be quantum computers. I'm not sure if it will be photonic ones. The question with quantum computing is that finally they have to cope in intermediate ranges with the compute speed of digital computers. So they have to fit somehow. For the Amdahl's law problem, they would fit, but we want to have them for many more situations. Yeah? Then, at this time at least, the fastest quantum computers are superconducting quantum computers. And of course, next step has to be achieved. You need a lot of those quantum qubits in order to get logical qubits, or at least as good as possible to go close to logical qubits. That's a real problem that people face at this time. There are some companies in Europe and in US that are very far advanced in this field.
Okay. Are there questions from the audience? Difficult to see. Yeah.
It's difficult. One cannot see you. You are in the shadow.
Just a very profane question, perhaps, because we have heard so many technical details, but what for exactly, for what purposes are the computers there, and who can use them? I would be interested to know.
Okay. So primarily the computers that we have in Germany, for instance, in Munich, in Stuttgart, in Karlsruhe, in Jülich, etc., are for scientific purposes primarily, but meanwhile they are also for the purpose to be used by industry, by startups. So at this time 10% of our capacity can be bought, yeah, for purposes of industry, and these are then projects that do not need to be published in an open sense. Yeah. But this is only 10%. Maybe it will be 20% soon. And the fields, the problem is, in former times I could say it is 4 to 5 fields. Now I can say I don't know a field that is not using supercomputers. There is really no field, because finally everything at least would use AI technologies. And if you want to make progress there, you have to construct a model. Take a prominent example is the human brain. If you want to bridge the white spaces in the human brain, at this time the only, let's say, viable way we believe is to get a frontier model of the human brain built from known data that can then extrapolate between the unknowns.
When we first talked, you gave me a really good example of how using the connection machine reduced the size of your programs. Can you remember what you mentioned when the CM Fortran came out?
Yeah. This was, I used to work on a very good machine. This was here in Karlsruhe. This was a Fujitsu VP400 machine. I liked it. And it had a long Fortran code to do all the loops and everything. So after removing all the loops, because you could just write for any loop one statement, or at least some nested of those, the code got smaller by factors of 3 to 4 or even more. Yeah? And so, but it also was much more transparent then. Yeah? So I could finally debug my original code by running it on a connection machine.
I think I remember the numbers were like you had 140 pages of programs.
We
reduced it to 20.
Yeah, 20 pages. Yeah.
So I thought that gave lay people a very good example of how much
this was roughly the ratio. Yeah. Maybe I was also able to write it more concise at this time. I don't know. Yeah.
Are there more questions from
the last one we can pick up?
So I keep looking at old computers, you know, vacuum tubes and everything else, where actually one of the biggest problems was mean time to failure for the individual vacuum tube. And now as we keep scaling up larger and larger and larger, is our ability to manufacture reliable components enough to keep up with that, or are we going to reach a point in which we just can't scale anymore because we can't manufacture silicon to be reliable enough to have long-running jobs?
Very good question. So far, the last 20 years, I was told every year by somebody, this is now the beginning of the end of Moore's law. Yeah? And 2 years ago, I have been at IMEC, and I said, where are you now? Okay, they said the official number is 2 nanometers as a structure. It's actually never the number that's correct, because the transistors are much larger, but as a minimal structure that you have on the system, 2 nanometers. And another guy said, but we are trying out 0.5 nanometers already. So you see, it is still unclear. The question is, do you have the right material to have no leakage currents and all of that? But the problem is another one. You can make certainly some progress still, but still you have a huge amount of energy to spend for doing this. That's the reason I say it's much better to go to lower temperatures, and it's the same company called IMEC who is doing this. So they have programs to look forward into cryocomputing, and I believe there you can make a next step. So there are claims that the same compute speed you can do with 30 nanometers cryocomputing structures that you can today achieve with 2 nanometers CMOS. We will see the compute speed, but much lower energy. Yeah? We will see if this is true. We will just wait 2 or 3 years.
Okay. Thank you, Thomas Lippert, for taking time out of your incredibly busy schedule.
It was a pleasure. Thank you.
And I have to say, the first time in last fall when I talked to Thomas Lippert and his Doktorvater Klaus Schilling, I was crying because I had for so long heard the connection machines were a failure. They were a failure. They were a failure. And then they were talking to me, telling me in glowing terms about how for them it really revolutionized their practice in scientific computing, and I'm still crying. Thank you, Klaus, for bringing the machines to Wuppertal. Thank you, Thomas Lippert, for continuing them and developing the legacy of the connection machines further. I'm turning this over to Daria for our next talk, which is interesting. That's okay, yeah.
So up next is Johannes Schemmel. He's actually our neighbor from Heidelberg, from the university, but he's today on a business trip, so he's joining us digitally. He leads the electronic vision research group at the Heidelberg University and is professor of neuromorphic computing architectures. His research interests include mixed-mode, very large-scale integration systems for information processing, as well as electronic design automation tools for mixed-signal system-on-chip design. He is the lead architect of the Spiky and BrainScale-S accelerated analog neuromorphic hardware systems, and his group operates the BrainScale-S platform within the eBrains infrastructure. We're glad to have him here with the online, with the topic Learning from the Brain, Neuromorphic Computing and the Future of AI. Please welcome Johannes.
Thank you for the welcome, and sorry, there's an echo. I try it again. Hello, everyone. Thank you for the invitation. I'm very sorry that I cannot be in Karlsruhe in person. It is an honor and also rather difficult to speak after a giant like Thomas Lippert, but I will try my best. We are doing much smaller things, and I will talk about more modest computer systems. It's about what is computing and how can we move more to the way like the brain computes. Originally, computing is something like this. You have an equation, you want to solve it, and the first computers were not machines, it were humans. This is a room full of computers before World War II. They computing the solutions for these numbers, the ladies here in this room. And obviously, they use their brains. So the first computers were human brains. And they took several seconds for this kind of compute, and the power consumption was maybe roughly 20 watts. So now we have machines to do this. We learned from Thomas that we have gigantic machines to do this. This is a small machine on the left that can already do this. You see the result on the screen. And this machine can do trillions of these calculations and also uses less power than the human brain. So why do we need to look for the brain for compute? This is because real-world problems are where the human brain demonstrates its power. For example, moving the body here of the football player or soccer player, look at what he's doing. And this was 10 years ago. And he can combine perception, prediction, and action in a fraction of a second within a very complex environment. And robotics is far behind these possibilities. But also this was, as I said, 10 years ago, and 10 years ago was also a turning point where computers become more brain-like using AI-based methods and neural networks, so methods that are inspired by the human brain. But still, these methods need a lot of energy. In this case, it was nearly 200 kilowatt hours to train the machine. That beat the world champion in Go at this time, Lee Sedol, and this was the last game where humans were better than machines, and that period ended in 2016. So now we have a decade since these events, and you all know that AI made tremendous advances since then. You all use ChatGPT or similar software. And I'm always impressed what's possible now. But this comes at a large cost. Here's a plot from Roland Berger, where they try to extrapolate the energy AI will need in the future. And maybe you've also heard this in the news, that there are now compute centers only for AI that consume a gigawatt of electricity. You see that already in less than 10 years, we will have more than all the classical data centers, more electricity needed only for AI. And if you look at this extrapolation in the future, you cannot really believe that this will come true, but that is what is planned. So people are building new nuclear power plants only to generate the electricity for AI. So we need some change in this, because we don't want to spend so much energy only for AI, but we still want, obviously, the power of AI. And we all know we have supercomputers at 20 watts. We have seen them before. That's our brains. And what are they doing different? So let's have a short summary about how the information processing in the brain works. In the brain, we have a lot of independent compute units called neurons, and they combine signals in space and time. It's very important. Everything happens continuously in time. And these neurons aggregate signals. They receive them from a complex interconnection structure. Each neuron receives approximately 10,000 inputs. And then they look at the temporal patterns in a continuous time fashion. You see here on the right, there's a voltage that is increased, which is signal received. And if it receives a lot of signals in a certain time interval, it, by a simplified view, it generates an own signal, so-called action potential, which it then sends out to other neurons. So it does a kind of a temporal spatial coincidence detection. And it does this in billions of cells. And this gives a very robust structure because information is always spread across a multitude of signals. Never is an information encoded in a single signal. It's always hundreds of signals out of millions of connections that carry our thoughts in the brain. And that makes this structure very robust. And it's also extremely sparse representation. From all these millions of connections, only very few transfer information at any point in time. And this leads to the high energy efficiency because of a super complex structure storing petabytes of information, but only very few active signals are traveling through the system. And that is where the energy usually is spent. So in contrast, classical computing is based on algorithms. The definition is an algorithm is a specific procedure for solving a well-defined computational problem. And originally, the idea was from Turing, how we can build machines to solve these algorithms. And the most, so the algorithm is encoded in a kind of a symbol chain of symbols. We called it tape. Now we call it memory. And the most important aspect was that von Neumann replaced this tape with the random access memory we have now, where all our algorithm data and instructions are stored. And so this so-called specific procedure in the definition is executed by reading and writing to this memory in a sequential fashion. And this sequential fashion is the biggest problem in traditional computing because it creates a so-called von Neumann bottleneck, because you always have to do this in one step after the other. So if a step takes a certain time, then the full algorithm takes the multiple of how many steps it needs with this time to perform the operation. So this von Neumann bottleneck can be solved, for example, by using this kind of parallel machines we have seen from Thomas. To summarize the differences, and you should remember the first computers were humans using their brains, and now we have the machines, that the basic mode of execution of a computer is serial compared to the brain, where all these neurons operate totally in parallel, and they operate asynchronous or in continuous time, while the computer does all in synchronized steps. You need to fill this tape with symbols, called a software program, to work while the brain learns from the beginning. It also builds itself. I mean, we all start with a single cell, and then the brain builds itself during development, and trains mostly itself by learning. And the processor and memory elements, also our brain needs processing and memory elements, but in the computer they are separated, and the von Neumann bottleneck limits the speed of operation. In the brain, they are more or less inseparable. Processor and memory are intermingled, and this is called in-memory computing, and therefore the brain is not limited by the memory accesses. It can access all its memory, petabytes of memory, more or less in parallel. And also due to this distribution of information, the brain is very robust. You can remove 10% of the cells. I mean, you might be not as intelligent as before, but you still can think, while the computer, usually if you change one bit, the software breaks down and you need complex error correction methods to keep it running. So we come back to the connection machine. Also, I was inspired by the connection machine when it came up. I was a high school student at this time, and I was very interested in computers, and I was totally fascinated by the connection machine. It was approximately 50 years ago, an early attempt to improve computing by making it more brain-like. I mean, it's not really nomorphic computing in our views. We will see this later, but I think the idea, he was inspired, William Daniel Hillis might have been inspired by this parallelism I just showed you. You can see the title page of his PhD thesis to the right, the connection machine, it's called already. And he envisioned a machine with a large number for this time. It was tremendous high number, 65,000 of identical small processors. They all execute the same program, each operates on a different piece of data. And this is called single instruction multiple data. And it is the same method used today in the NVIDIA GPUs that are the basis, you have seen this by Thomas in Thomas' talk, the basis of our AI technology. So this was groundbreaking work. And due to the distributed way, the phenomenon bottleneck is very much reduced. It's not eliminated in this kind of machines. You still have processors that operate sequentially, but you have not one, but 65,000. So it's already reduced by a large amount. Here you see an illustration from the original thesis, how this can be envisioned. You have a problem. This is a parallel problem. You want to calculate you want to analyze an image. This image is two-dimensional, and so you can distribute this on a two-dimensional grid of processors to perform the necessary calculations in parallel and not one pixel at a time. And now the nomorphic concept, which wants to take this further, going closer to what we have learned from biology, what I've showed you, learning from nature to advanced future computing. And the motivation is always twofold here. It's not only future computing based on biological information processing, it's also that we want to understand the biological information processing. So we also want to model the brain by using this nomorphic hardware to understand our brain, but also we want to learn and be inspired by the brain how we can do better information processing. Like AI is already inspired by the brain using artificial neural networks. So these are the two of what I just said, about examples for these motivations. And both requires circuits and architectures for scalable nomorphic computing systems. Like you need the big computing machine if you want to do scientific computing. And you see here two pictures of modern implementations of highly parallel machines. To the left, you have a system with millions of processors on a very big silicon substrate. It's cut out from a silicon wafer from Cerebras. And on the right, you see these NVIDIA systems Thomas also told you about, they use in Jülich, for example. And these modern implementations of highly parallel machines, they are used for AI, but they are only an intermediate step to nomorphic computing. They are still not what the brain really does. And this is what I want to show you now in the remainder of the talk, the approaches to these goals. So the basic principles of modern nomorphic computing are that you have a lot of individual compute elements called neurons. They represent somehow the biological neurons, and they are interconnected with each other, and they do really in-memory computing. So each of these compute elements has their own memory connected with it, and it overcomes the phenomenal bottleneck between memory and compute by this method, because you have the same degree of parallelism than the brain. That's the final goal we want to reach. And sorry, I was the first. And there's no separation, that's very important, between the algorithm, what's called software, and the computing substrate, because the memory and the compute is the same. So there's not a program in the memory and a processor that executes, but it's really parameters that shape the system, that define the network, or in the biology, it's what you've learned in your life that defines your brain. And this, together with the compute of the neurons, that defines what your system can compute, or the neuromorphic algorithm. So the algorithm is imported in the substrate, and the memory content is intermingled with the compute neurons. You cannot separate this anymore. For example, you can also not, in a final neuromorphic machine, you also won't be able to transfer memory content from one machine to the other, because all small, the memory content is really adapted to the compute units, and they might not be identical, and therefore you could not just take out the memory content and move it to another brain. And to make progress in this area, there was different research projects. One of the most important in the EU was the eBrains or Human Brain Project that led to the eBrains project, where a research infrastructure for neuroscience was developed for all scales of brain research. Also here, the machine in Jülich is one of the most important parts of it. And one part of it is to build neuromorphic hardware that can emulate brain tissue on like it is really operating. So not in a softer fashion, but really build a model from it. So we have this brain, there were different parts of computational neuroscience technologies in eBrains, but one is the brain-inspired technologies. On the right, you see two compute systems that were built, and for non-experts, they look similar to the compute systems Thomas has shown, but they are in fact really very different from the inside. And there were two different systems, the Spinnaker and the BrainScales machine. The Spinnaker machine started in Manchester in the UK, but now it has moved to Dresden. So both machines are now in Germany. And Germany is therefore, regarding neuromorphic computing, really at the, very far ahead worldwide. Very much in contrast, for example, to GPU development, where we have nothing. And you see the differences, and the machines are very complementary. The Spinnaker machine is a digital one based, very maybe similar to the connection, to the idea of the connection machine. It has a lot of processors, very small ones, very simple ones. Each processor can more or less calculate a few neurons, and they have a special network that allows them to communicate in real time the spikes from the action potential from the individual neurons with each other. And the BrainScales machine is a so-called physical model that will explain very soon what this means. So we have a many core architecture that does brain simulation, and there's a physical model that does brain emulation. And this is maybe different from what most computer experts in Germany do here. The chips were really developed from the transistor up. So these are really new developments on a circuit level. The Spinnaker chip here you see is a digital multi-core neuromorphic computing. You have a high number of small processors that give better energy. That follows, as I said, the computing, the paradigm of the connection machine somehow. And then you use not only one chip, but thousands of these chips to build kind of a large neuromorphic computing system. But it's still limited by the phenomenal bottleneck and the serial operations of the processors. It's similar to the connection machine. It improves above this bottleneck, but it does not eliminate it. And why is this important? Let's look at the energy scales. This is one of the most important goals for all these developments, to reduce energy consumption. And if we see at the top of the energy scale, we have the supercomputers that consumes in order of joule of operation, while we go down to the brain where we are in the femtojoule range. And now to illustrate what this means, imagine one neuron in the brain that receives approximately 6 million events per minute. So this is just what's happening in average in your brain. And now imagine you heat water with the energy this neuron needs to process these 6 million events. And if you are at the level of a modern supercomputer, then you need roughly 10 to the power of -4 joule. So the water is already heated 1.4 degrees in a minute, only by processing one neuron. In a biological neuron, this is only 10 to the power of minus 14. Now, let me scale this up to the full brain, and you see a human brain needing the energy of the supercomputer would reach in 1 minute 100 billion degrees Celsius, so totally unfeasible. In the human brain, it's approximately 11 degrees of Celsius, and that amount of heat is carried away by your bloodstream, so it's no problem to cool this in the biological case. And neuromorphic computing now allows us to go far below the power levels of the digital systems, and we can roughly reach levels of 10 to the power of minus 10. So we have an energy saving of more than 10 millions compared to the digital solutions. And now, how is this done? What is the difference in concept? How can we reach this? The basic is already we need a model for the neuron. And in artificial intelligence, for example, you have mathematical models and digital or numerical solutions that then calculate on this. But you can also use a physical model or a physical solution, which is an electronic circuit that performs similar to the real neuron. So you do not use numbers to describe the operation, but you really build a miniature version of what the neuron does with transistors in the chip. So you mimic what's happening in a biological cell, for example, like the charges traveling through a cell membrane. And they create voltages across the membrane, and this is emulated here by these components like a battery and a resistor and so on. And this gives you a natural representation of time. And also the nice effect is that you can easily build an accelerated neuron model if you just have slightly higher currents than biology or smaller capacitances than biology. So you have this physical model circuits, and now we have to make them parameterizable. So we add changeable values like depicted here by this potentiometer. And then we use signals from the system itself, like, for example, the temporal differences between an input and an output signal to adjust these values. This is so-called learning signals we derive from the network. But we can also use learning rules like in machine learning, like gradient descent. So we can also train this. At the end, we use all this kind of learning or training to adjust the parameters in this physical model to build some kind of an artificial neural network system that does not use any numbers. It is really only based on physics. Here's an example. We build the brain-scale neuromorphic processor. And if you then have this kind of system and you have the training or learning methods in place, you can train this network to solve problems, like, for example, doing image recognition. In the future, we'll also build large language models from this paradigm. And thanks to the fast analog neuromorphic processor, this takes only microseconds. So in principle, you have the same kind of operation like in a biological brain, but you can speed it up orders of magnitude. This is an example, this is just a picture showing you how these chips look from the inside. We have all these small transistors here that mimic biological synapses and neurons in a direct manner, also without using any numbers. This was this research we started here in 1995. I want to show this slide to remind you that this group was founded by Karl-Heinz Meyer, who passed away in 2018. And since then, I leading this research group. And we started this also we started this also long time ago, 1995. So we went through several generations. And one of the most recent generations I want to show you is the brain scales one, where we used full wafer, silicon wafer, to put a lot of these analog neurons together in a system to build at the end a similar kind of high performance neuromorphic compute system as Thomas showed for the digital systems. They are now located in Heidelberg, in the new Heidelberg I Institute, the European Institute of Neuromorphic Computing, where we have different generations of these systems mounted in compute racks. It looks similar to normal compute centers. Here you can see the BrainScales 1, where we have this wafer in the center beneath some heat sinks here. And this is the BrainScales 2, where we have more separate single chips in compute racks, more than normal computers. And I won't go into details here because I have not that much time left, but just show you one important aspect here, that if you have this high number of physical models, so we have more than 20 million neurons on this, and 50 million synapses, you can implement a lot of complex models from neuroscience and evaluate them, and you reach speeds of terasynaptic operations per second. This is while still consuming only very low amount of power. And this is here a comparison from a publication where we compared it with different other systems. And even if this, without any optimization yet for energy, it is already regarding the energy per synaptic transmission much lower than all the digital systems available. Just before I conclude, one example what you can also do. This is not all for biological or neuroscience research. Here's a very practical example where you use analog neuromorphic computing for optical communication. If you transmit information via an optical fiber, you see it here, then there are some nonlinear effects in this fiber and the information gets distorted. And then if you want to receive, if you want to read out the bits, you need some processing to separate, to make this distortion, to reverse this distortion and be able to discern between the different bit patterns. And this needs, because of the high speeds, a lot of energy. And if you do this with an analog neuromorphic system that is fast enough to do this directly in real time without any ADC or digitization in between, you can directly convert the light to spikes and use the spikes in the network to to train the network to detect the original bit patterns. And we did this, and we were able to show that you reach similar performance than the traditional methods, but without the complex digital communication necessary for the digital traditional methods. And to conclude, one of the most important aspects of our systems is that they are not only for us, but they are open to the public. So Heidelberg operates the only analog neuromorphic cloud in the world, and this is what we are proud of. It's part of this eBrains neuromorphic computing services I mentioned, and you see here two examples where you can use this analog neuromorphic system to do all kinds of experiments. For example, to the left, you do some learning experiment, some learning experiment, and to the right, you just model some neurons to study their dynamic behavior. And all this is possible for everyone who is interested. You just have to go to this website and get an account, and then you can use it for free. And that's, with this, I want to conclude this talk. Thank you for your attention.
Yeah, thanks a lot, Johannes, for the very inspiring, nice talk, giving us a future of computing. And of course, when I hear this, so you already founded a startup like Thinking Machines, and we get these things, or what is or other way around? What do we need? Because this is a new way of computing. Yeah, what would we need to make this a new type of company? As in former times, Thinking Machines just came up with a new idea and then said, okay, here's the machine which can do something which nobody else can do.
It's already happening. The Spinnaker system is a startup because they are closer to classical systems. It's always this hen and egg problem. Since the paradigm is different, you need people who have learned how to use it. And so for the Spinnaker system, which uses a paradigm which is closer to parallel computing, they already have a startup, and a lot of, also Jülich, for example, we get one, I think, and also other places get this machine so that people can do research with neuromorphic computing. In our case, I think it is still more basic research oriented. So we have a research platform which is just non-commercial and open for everyone to try out. But it's very likely that in the upcoming future, this analog processing ideas will also be commercialized for some applications, for example, like this optical communication or similar applications where energy efficiency is paramount. But I'm very sure that in the long term, it will also replace traditional computing in the compute center, for example, for large language model inference or similar applications.
Okay, so we learned today that one of the things that make connection machines so interesting was the way to access it, because it also sort of due to the easy way to program it lowers the border for those that have application to access the machine. So how is this now with neuromorphics?
Yeah, this is why we spend so much effort to create this public platform in eBrains, because traditional computing has 50 years ahead of neuromorphic computing. So all this, since everything is different if you have a time continuous paradigm, like neuromorphic computing, it needs a lot of trained students and trained experts to make use of it. And to make this easier, we created this eBrains platform where we have a more or less standard Python-based software interface for the interested people to learn to use it.
I see. Are there questions from the audience? Well, there are.
I think Brewster was first, so we'll start with you.
Did you say what the the wattage, the power requirement decrease was for your being able to read the high-speed network signals? Was that less power on your eBrains?
For this communication?
Yes, for that application. I must have missed it.
We demonstrated this with our existing platform and did some estimates for professional implementation. Since to use it with real optical communication, you would need a speed up of approximately another million, because we are talking about gigahertz. So we did the emulation in the real system, but with at a slower speed. But the energy efficiency advantage was approximately 10 to the power of 6. So it's tremendous.
Another question here?
So when you say in the long run you see this being able to run LLMs and yeah, whatever AI does, then what do you mean by long run? What is your perspective there?
It is mostly defined by the access to capital. I mean, if you follow the traditional developments, sorry, I have an echo here. It's really difficult to talk. Can you switch it off? Okay. So in the traditional AI world, the development speed is also controlled by the capital. And you know the billions of dollars now invested in this, and that accelerates development a lot. And here we need some breakthrough applications so that the funding and the development is paid to start building these machines in large scale. And then I think it will accelerate, because the energy efficiency and the savings will pay for itself in the medium to long term. So I would assume that we will have systems in the compute center in 5 years or so, 5 to 10 years, like what Thomas Lippert said when he showed his slide with the quantum and neuromorphic at the bottom. And when it will be taken up by AI companies, I don't know. I mean, I'm not an expert in this.
Are there more questions? This seems not the case. Everybody is looking for refreshment. So thanks again for giving the talk and also for answering the questions.
You're welcome.
So now we will have a short break till 6:45. And I would like to ask all the speakers to stay in the room because we are going to take a group photograph. We'll take a couple of minutes.
Recording stopped.
Is this on? I don't think it's on. Is this on? Yes. Are we on? Are we going? Thanks for staying with us the whole day. It's been a long day. And you probably know now more about quantum chromodynamics than you thought you ever would. And that's who I want to start with. I want to start with by introducing Klaus Schilling, who is on stage for the first time. Let me see if I can do this with one hand. No, hold on. There we go. So, Klaus, can you wave so people? There we go. So, Klaus Schilling is a theoretical physicist whose work has focused on quantum chromodynamics and lattice gauge theory through computer simulations. After studies and research in Tübingen, Bonn, Hamburg, CERN, Caltech, and SLAC, when were you at SLAC? I missed you. He became professor at the University of Wuppertal. He co-initiated major research efforts advancing lattice gauge theory on supercomputers, including CM2 and CM5 systems, and led a research group in Jülich. Please join me in welcoming Klaus Schilling. So I think that Thomas, your doctoral student from long ago, mentioned a little bit about... Still today. Oh yeah, that was today. Mentioned you, but can you tell me why you brought connection machines to the University of Wuppertal?
Yes. It's a little bit a longer story. Because I started as a nuclear physicist, being interested in nuclear energy at the time, in the 50s. Nuclear energy was a big issue and a great perspective. And when I got into the details of theoretical nuclear physics, I found it was a mess. I mean, there was no real theory because it's dealing with strong interactions. And there was no way in coping with a strong interaction problem. In contrast to electrodynamics or quantum electrodynamics, where you can use perturbation theory, which was, by the way, introduced very, very much by Feynman, who was quoted here so much. He got the Nobel Prize for that, Feynman, shortly after World War II.
Dynamics deals with the particles.
Yeah, I'm coming to that.
Okay, good. I was afraid you were already past that.
I should also mention, introducing myself, that I spent a year at Caltech, and the reason was that Feynman and Gell-Mann, all these great figures, were teaching there. So I followed actually the lectures of Feynman, even as a postdoc. The postdocs went there. So I had contact with him. And the point is that in 1973, there was a proposal of the theory of strong interactions, namely quantum chromodynamics. That happened in 1973. And that is a theory which is very beautiful. In fact, I should say that word here because we are dealing with art. It is very similar to quantum electrodynamics, but generalizes it. I cannot go into details. It's a generalization of quantum electrodynamics. And the point was how to verify that theory. And then famous theorist, later famous theorist, namely Ken Wilson, he started simulating that theory. And he was claiming that could only be done with IBM. So we all knew that Ken Wilson went for 1 year to IBM in Zurich to solve that problem of QCD. What is the problem? The problem is you want to compute the spectrum of the observed particles, strongly interacting particles. Once you have computed that spectrum, in accordance to empirics, then the theory would be established. Similar to atomic physics, which was proven by theoretical reproduction of the atomic spectra. Okay, that was our problem, and soon we started conferences within Europe and together with the Americans, and it was clear that we needed bigger computers. So I remember panel discussions like these here that happened in Brookhaven, 1985, where first groups in theoretical physics started to build their own computers. There was in particular the theoretical physicists in Rome under Giorgio Parisi who built their computer. I must say I did not feel strong enough to do that, not enough competence. But then at a conference in Chicago at Fermilab, I met my old friend Claudio Rebbi from Boston University, and he told me that they would purchase a connection machine. And I remember I came back to Wuppertal. I was very excited. I need one such one machine like that, and went to the chancellor and all over the place, and we tried all sorts of possible funding for that machine. And in the end, we convinced the Deutsche Forschungsgemeinschaft to buy that. And so it turned out that we became the only German university to run a connection machine. There were others, but they were in research centers. And then something very strange happened. Well, I should, another remark, when we got the machine, when we got the funding, our computer center said, okay, we take care of it and we will run it for you. And I said, no, we want to run it ourselves because we want to learn more about computing. And then thinking machines was a very great company because it was carried by young people. And it was not hard to convince them to have application engineers locally. So for many years, we had people from thinking machines. Some of them are still, yeah. And Thomas mentioned Terry Dontje. And also, I think Guian Barnot was with us. He was working. He was working with us. Yeah. Yeah. There was Eugene Lowe. He was another one. Yeah. Yeah. So that provided a very good situation for us, and many students liked this, and so students came from other universities to work in our group. It was just the correct moment in time.
Can I add to that? One thing about, because I think that was, I wanted to correct something I think that Danny said earlier, that we were not led by customers. Maybe initially that's true, but very quickly we realized that our customers were giving us much more information back than we didn't know QCD. We didn't know weather prediction. We didn't know what was needed, so that we did put on-site engineers largely as not just to take care of the machines, because they actually did take a lot of maintenance,
bi-directional spies.
But we got information back, so much that guided our development. Particularly, I mean, hardware has a longer cycle, but software, so we could come up with CMSSL. We could come up with a lot of the libraries, parallel ray tracing, which got us into computer graphics. A lot of that was coming back from our customers. So after, I think, the initial founding or whatever, then I think we very much were driven by our customers. Unfortunately, our customers were primarily national research labs, and that marketplace is a lot smaller than like a commercial marketplace.
Yeah, and there is another line of development which happened in the 80s, it was clear that in Germany we didn't have the sufficient computer power to compete with our colleagues in the United States, because our computer centers were not adequately equipped. So we made, from the universities, we made an action that we needed a supercomputer center in Germany, and we were able to convince DESI, the National Accelerator Center, Particle Physics Center, to support that. And that was realized in Jülich, and DESI was willing to establish a physics group doing computational particle physics in Jülich to foster the interaction between computer science, applied mathematics, and theoretical physics. And that group was established in 1987, 1988. The whole construction was called Höchstleistungsrechenzentrum Jülich, which was the precursor of the institute that Thomas is now heading. And that happened in parallel. And then to add another little story to that, when I was offered that position, DESI asked me whether I would like to go to Zeuthen, because DESI in Hamburg had a branch in Zeuthen, which was a previous research base of East Germany before 1990. And I said, no, I want to have an interaction between the Wuppertal group and this Höchstleistungsrechenzentrum. So I decided for Jülich, and then we had a very lively interaction. So I think I've made enough words.
Here on stage, do you have anything you're kind of bursting to get out after getting all of this input? Before we start peppering you with other questions, does anyone? That sounds like a no. Do you have questions?
Well, of course, I have a lot of questions. So one, yeah, I guess so. So one question which sort of remains is, we heard a lot about what has been inspiring from the connection machine towards the computing that we see today. But every now and then, every 10 and 20 years, we find another principle from these inspiring machines, whatever this was, that has not been detected so far, but is now inspiring the next wave. So I want to hear from you what this could be, because you made it and you probably have ideas. What has not been, from the conceptual perspective, from the technology, has not been used so far, but would be a potential for future computing systems?
I could just, one little thing on that. It's been a real surprise to me over the last 5 years in AI with the growth of LLMs. And we just did not envision that, because we didn't know, just simply by scaling up in the amount of data and the amount of size of these systems and training for hundreds of millions of dollars to compute, could you get to what ChatGPT is doing today? We were using a lot, so that's why the whole history of AI, I think, is kind of a funny thing to try to analyze, because I think that was a surprise to everybody. It just took a company with a lot of money and a lot of guts to say, we're going to do that big experiment. It might cost us $100 million to do that one experiment. And they discovered something, that these things don't work until you actually get to that scale.
That brings us to maybe another. Yes, please.
May I answer a little bit your question? At least in the sector, I believe one could explore or should explore more. So I have this is connected with an anecdote. When I was going to my first conference as a PhD student in London, This was Parco 1991, I remember, I think. The Parallel Computing Conference gave a talk, and there was another guy giving a talk who was, of course, very famous. His name was Gustafsson, Dr. Gustafsson, and I got into a discussion with him where he finally blamed me not to know much, yeah, in the public audience. Which was true, yeah. So clearly, but I'm sure he was wrong up to now, yeah. In terms of what he was proposing, it had to do with his famous, meanwhile famous law, and so I got obsessed over 30 years solving Amdahl's and Gustafsson's law, or have workarounds that. I think one dimension that has never been explored properly is the fact that if you go to the simple Amdahl's law, you can assign to the scalar or serial part a processor with a very high frequency, and to the others you can do stupid GPUs. You scale them up to infinity, but the other one, or the, let's say, can be a smaller machine, would have a very high frequency. So there is a factor between the two processors which goes immediately into the speedup. The speedup is multiplied by a factor f. This has never been done. So this highest level of functional parallelism is some unexplored computational science thing. And I believe here one could do much, much more. So imagine you have a terahertz processor. You can, in the principle, solve the Amdahl's law for strong scaling, and it would of course have also a lot of impact on Gustafsson's law. So you asked this question as a computer scientist. I believe this is unexplored field. One could do a lot there in this field.
We need a quick explanation of Amdahl's law for people who don't deal with it on a daily basis.
That's a law, so maybe you should know. Yeah, okay, so Amdahl's law. Amdahl's law is the fact that if you have a part in your code that cannot parallelize, let's say it's half of the code cannot parallelize and the other half of the code can parallelize, and you use the same processors for everything, then the speed up through parallelization is limited by a factor 2. You cannot go over a factor 2 speed up if half of your code is serial. Okay, if it's 10%, then your speed up is 10. If it's 1%, your speed up is 100. But if you can speed up the scalar part even more by using a different processor, you can multiply by a factor of f. So if the difference is a factor of 10, it is even much more. You can go up to 1,000 to 10,000 depending on which type of processors you use. That's Amdahl's law for strong scaling. I hope you understood it. I'm sure it was much easier than to understand any lawyer on real laws.
I'll take unrealized dream for 10. Okay. So we have a lot of the pieces of that dream of AI from a long time ago, of the what could we do if we could make all of the knowledge come to life? What could we do if we could build the library we've all dreamed of? What could we do if we could make the Library of Alexandria come and anybody could talk to it? And we've got a lot of the pieces, but we haven't put it together. So why were libraries? Libraries were places you could go that had things you couldn't get at home, whether it was books, but also access to librarians, the other people that were hanging around in it, and interesting facilities. So imagine a room like this that were all screens that had information all over it, with people going and playing and doing interesting things with the information, both that you could learn from what other people are doing, but also because there are librarians there, that we basically have all of the works, all of the published works of all of humankind, which we almost have now in the public sphere. In the private sphere, it's all nightmares and lawsuits and problems and blah, blah, blah. But in the public sphere, especially in Europe, we could build that library. So we have the computing now. We've got all the data. We actually have, the LLMs make it so you can interact with obscure journals from whatever. You can go and find pest records from Sri Lanka from 1953. You're not going to read that, but your computer will, and it can incorporate that into how you're interacting with these systems. So I want the library, and I want it in the public sphere. I don't want it to be OpenAI is going to go and shitify it and go and make me buy the wrong pair of shoes. I mean, blah, we've seen that movie before. Let's go and do something better this time with our new trick, which is the AI stuff that is actually able to be used in something new. That's the unrealized dream that I think we now have the pieces out of all of the work of the people in this panel and also within Europe to go and build something really mind-blowing that will be remembered for centuries.
Could I answer the Amdahl's law question? Because I think it's based on a false premise, which is that if you take a algorithm or whatever and you say it's these steps and a certain number of these steps cannot be parallelized, which may be true, but the false premise is that you can't solve 1,000 of those problems at the same time or 10,000 of those at the same time. And that's what data parallelism is partially about. If you can't solve it purely in the data for that one problem, take 1,000, if you've got 1,000 processors, get it so that the input system can get you 1,000 problems to solve together.
This you can, but if you have a problem that cannot be parallelized at all, then you cannot do it.
Digits of pi.
Yeah, just for instance, deterministic peptides. We try to simulate this. You need one serial processor. Of course, then this is an extreme case. You cannot parallelize anything. Then you have to speed up. And that's the point. Finally, we need to get to larger frequencies in the processors. Okay, let's go to cryocomputing. I said it before.
I want to go back to Brewster's comment, because on the one hand, the access to all this culture, all this knowledge is amazing and exciting, and it feels like we're getting very close. On the other hand, there's the very real fear from artists, from visual artists, from writers, from people who create new content. And I saw a cousin of mine when the first, I think it was Midjourney came out, and it turned out that he made his living by rendering backgrounds, two-dimensional backgrounds for two-dimensional computer games. His wife worked as a production manager at IBM Xbox, and he wasn't very eloquent, but he could draw really well. And his wife couldn't draw at all, but she was really eloquent. And at that point, when Midjourney came out, she in 2 minutes could create an image that he would need 2 months for. He stopped working. And that was like the first very personal example of someone who, with that change, immediately had no market for his creative skills. Can you address that, and how you think that we can deal with that, so that access to content doesn't mean denigrating creative output?
Actually, it helps. The libraries are publicly funded entities that buy things from publishers that are supposed to pay authors. In fact, they don't pay them very much at all. This is a real problem. And so let's go back to actually paying authors. It's about $20 billion a year in the United States is put into libraries. About 25–30% of that goes to publishers' products. Right now, it stops with the middleman, as I just said. But those dollars were socialized investments in culture, and often a lot of local newspapers, local publishers, local authors. All of that's gone based on corruption of the publishing structure. But the library system is there for the public good, and that floats a lot of boats. It's not going to make every graphic designer suddenly buy the next generation Tesla. No, but it is going to go and make it so that academic publishers, academics can go and publish openly. Would be awesome, with good-looking materials and books that are designed and the like, and have a flow of information again, where we're building a lot of constriction points, And let's just not have it go through a few players. Let's go through a lot of players. And the library system, actually, if we reinvigorated it and reworked with that class, it's not dead yet. People still believe in it. It's just being hollowed out in terms of what it can do. If we put in a good jolt of technology, if we could go and make some interesting things out of it, there is the money to go and support the creative class at some level. They may not be making tons of money like Mad Men. That'll be going through, I don't know, people that sell drugs or wine or, you know, whatever. But for cultural heritage, I think we got it.
Are you talking with any governments or institutions about implementing this idea?
Yeah, they're all looking for it. They're looking for how to go. They have these spaces. They have the people wanting to come in. But we have the technology. They're just not being matched up. And I think Europe is interesting because it's got a sense of the public sphere that is being lost in other parts of the world. For instance, the United States. So let's go and do things within the European norms using our new trick, which is these supercomputers that can go and do interesting things with it, to live the dream that a lot of us went into this for 40 years ago. We have the pieces.
You're talking about libraries.
Yes.
That you assume a certain truth behind all the contents in the library. But of course, there is always opinion. I mean, if you look at history, any history, German history, European history, American history, there are many historians who have very different opinions.
I want the books to
and that's one of the art of mankind, to differentiate between these opinions. So you have to, if you have one library that makes it all flat, you have another truth. So there is this question about opinion and truth and attitude towards so-called facts. How would you deal with that problem on the level of large-scale computing, AI?
I would like to see books debate each other.
Yeah.
Really? So, you know, let's have Marx debate Spinoza.
Yeah.
We can do that now. Let's go and have it out. Let's go and actually start to go and find patterns within the data that we can't find in other ways. I think that you're absolutely right that if we just trust, you know, if it's in the library, it's true. That was always stupid. So we have mechanisms to go and move through this data in new and different ways, and combine it in new and different ways.
So I can challenge. I can question the AI with certain eyeglasses.
Sure. I mean, you can go and start to research.
From the conservative point of view, from the Marx point of view, from Hegel's point of view, or whatever, ask about history.
You could know something about every author and all the rest that they've published. You know, because you pull a book off and it's kind of atomic.
Yeah.
Right? And what you really want to know is, what else did they write? And who did they learn from? And what's the family tree of where they came from? All of that's completely doable now with our computer structures. I think we can make the data come alive in new and different ways. And the cultural heritage here in Europe is deep, and people are proud of it. And they want to go
differentiated, yeah.
And it's a differentiated. And let's go and go and make it so it works in every language. Let's go and make all of these, because it's going to be lost in the commercial melee of going for more, I don't know, whatever OpenAI is going to do. I don't care. So why don't we go for something that's finished, that really thinks in Finnish, right? Or how can we go and make it so that our kids are educated in new and different things? We have the tools now between the supercomputer centers, the new ideas, and the data. Anyway, that's my...
So I have a bit of a provocative question to that. You know, why stop at the printed matter? Why don't we go on to data observations and something we're actually going to go, what about all these simulated data? We are generating tremendous amounts of data with the supercomputing centers that are usually lost. We don't have, there's a term called SDL, Simulation Data Lake. There is you know about this, there are European projects also. But there is wisdom and knowledge in that. So of course that immediately, I don't know what number, what factor that puts on your, probably you would have problems fitting it on your external disk there.
Yeah, I would agree. I think one of the disappointing things about where we are in AI today is that it started out of LLMs. And instead, my hope for AI from 40 years ago is that it would be used for science. Science, medicine, global health, environmental issues, and that means it's not just relying upon what we printed already, it's exploration. And that's where I'm hoping that we start to use some of these large systems really for science that's actually relevant to the world today. So QCD is nice, and everything else for the physicists and everything else. But for the rest of us, I think understanding climate models or predictive kinds of things, if we can build that in, then we'd have a lot more educated public, because they could start to make questions, scientific questions, and see if we can get answers out of an AI.
Yeah, the interesting thing is that it was just mentioned that these synthetic data from theories, that they are infinite. Yeah. So one can, in principle, train a model. I've just heard of an initiative that wants to get all molecular dynamics data that are existing in the world together in a frontier model. I'm not sure if this is really possible. Yeah. And what can it finally do? It can predict for most of potential molecular dynamics already in its solution what it is. So if you extend this further, you can imagine a world where everything that has been formulated as a problem to solve, differential equations, is in a model that's solved. Yeah, we only given it an input and it out comes the right output. Think of some physics theory like electrodynamics. Yeah, it's of course utopic in a way, but this might come. And so I believe that all of those synthetic data through simulation finally can be used to form models that already represent solutions to many problems, that as many as you can think of.
Are there questions from the audience we can take at this point? Do we have a microphone on the floor?
Thank you. Okay.
Schon geschehen, danke.
I find this conversation interesting, but I can't help feeling that one thing that AI has not yet addressed is actually a functioning epistemology. That's a problem we have not addressed. And until we have that, I have said before, but I feel sometimes looking at the current situation that there are several physicists on the stage, okay? About 100 years ago, Sadi Kano explained that there's a limit to how effective you can build a machine, okay? And I feel that the work of people like Judea Pearl says exactly the same about how far we can go with current technology. And I think that insights like Pearl's are insufficiently taken account of in current discussions. That's my
maybe AI can only reflect, let's say, depth in complexity that is also represented in its data. Yeah? The real question is how far it can go beyond. So I have the feeling that the real brilliant ideas are not so much represented in our world. And so the AI cannot be fed with really this process of brilliance from so many sources as it can be fed with all triviality. So, yeah, so the triviality is in a massive, let's say, has a massive dominance over real brilliant things. That might be a problem. Of course, it's a question how we train them. Yeah? So we have it in our hands.
But in the end, you cannot get insight from observational data. And these gadgets work only
I doubt
from observational data.
So all physics is insight from observational data.
No, it's not.
Oh, it is. we can debate it, of course.
Happy to.
Yeah. Yeah. The hen and egg problem.
Probably one thing which was also brought up several times and would be interesting also to probably have a common sense is we are talking now about LLMs, which is very high level. Yeah, so the access to the system is mostly on text based, and but you can also fit in, of course, formula, etc. Sometimes he even sort of understands what is going on, so in a very abstract manner. On the other hand, connection machine, the beauty was it's very simple to program. Yeah, so we have a lot of things in between. So what is the right abstraction layer for feeding in now the machines? Is it now really the way we interact now with LLMs? And even agentic AI means that you have a lot of LLMs that talk together, and they use this because they come from different sources which are trained on text. They use the text to communicate with each other in contrast to function calls or whatever which we have done before. So is this the right abstraction layer of now? Is this now the new beauty, or is it still the programming?
Maybe you can address the question, how come some people say parallel programming is very easy to do, and some people say it's impossible to do and very hard?
Actually, I think, Bruce, almost everybody I know is now using Claude or something else to write code. And because all the minutiae of writing code is so hard. And whenever I approach a new problem, I had to figure out how to run something on Oracle's cloud, and I don't know their API, and I don't know their commands, and I didn't want to learn it either. But I can use a LLM like Claude or ChatGPT to do it for me. And I sit there and I still have to design what I'm trying to accomplish. And now I'm more of a program manager than writing code. And I'm sure people who are writing parallel code will be using the same kind of interfaces. And I think that's right. So I think it's helpful that way. To me, it actually questions, we're training large LLMs on vast amounts of data, and that gets embedded in the model, as opposed to a human's not born with embedded knowledge. A human learns through experience. And so memories, in fact, become what we learn. So I'm actually interested in working on now, how can we use memories to learn so that ChatGPT or whoever I'm interacting with remembers things forever about me or whatever I need, because it stays in memory. I'm not rebuilding the model. The model is basically what it was born with. I just need to be able to have it learn over time.
I agree that we now have tools to make it so that these vast computing resources are usable by mere humans, which is kind of great. And the idea of processing, Planet Labs is basically photographing every square meter on Earth every week. They have low Earth satellites, and they've offered that to go and put into these public AIs. So it's going and saying, no, it's not just text-based, it's vast amounts of data can be put into these computer systems, and then you can ask it questions by people or write these programs. And we're now seeing at the Internet Archive a lot more use of the Internet Archive by bots. And some of them are strafing us so that they can build their own models, and some of it is just basically people going and writing stuff and hitting the library at a phenomenal level. So we're putting out hundreds of gigabits per second, and it's going up fast. And we think it's bots. And let the robots read, right? Come on, that's what it's for. And so if we have to go and cordon off the copyrighted material so that those things are not there. But all the government data, all the public domain data, we're starting to see the bots come to life. We think that there are people behind them. Maybe, we're not quite sure. But our environment is changing fast. The ability to digest huge amounts of information based on the connection machine supercomputer structures, now applied in the small and the large, has made it so that we've opened the doors for computer-assisted help.
That also includes, of course, computer-assisted surveillance, which is something that in the U.S. we are realizing doesn't just happen to other countries, but is happening in our country, and that can be the use of AI to turn our country into a fascist state is progressing at a good clip. How can we counteract that?
May I just make a statement? Werner Herzog made this wonderful movie, Lo and Behold, with Danny Hillis featuring. And something that I keep telling people is a scene where Danny Hillis says, well, you know, at the beginning, we had these email addresses, a book like a phone book. And I went through this phone book of email addresses, and basically I knew all of those people. And that, combined with the spirit that I see from you who were there at the very beginning, is extremely positive. And there is no fear that anybody would have the idea to actually do something bad with it. And I think I understand that's the reason why the way the internet developed without any real strong mechanisms to keep somebody from exploiting this in a bad way, and here we are decades later with all these problems. And to me, the question was asked at the very beginning about the evolution of hardware. I mean, I'm not a computer scientist. I'm much more concerned about the soft side of things. So, where do we go, and what does it do to the young people now? At universities, they will use AI all the time. Our kids, they will grow up with this. How will that change the way we learn? And you made a statement. How happy you are. You learn from interacting with AI, but it also keeps does it keep young people from generating the stamina to actually fight for knowledge in a way, at a time when you get immediate response to very complicated questions, which we went to a library, we went through different books and here there and looked for references. That's to me is a question we cannot solve and not predict what's going to happen. But I think the way 5 years ago when I was surprised that AI would recognize if I say a word in my very broad German Swabian accent, it recognized the word. I said, wow, that's amazing. And how far have we come in this? And what's the rate of change in the next years?
I'm also seeing in my circle of friends a very real problem that young people graduating with computer science degrees can't find jobs. And the ones that go on and get PhDs in AI, they're getting really good offers. But the ones who are just kind of like normal people doing normal CS programming degrees, there's no entry way for them right now. Do you want to say something to that?
There was this term that was put out that I really like, which is AI washing, which is sort of blame anything on AI. Everybody can't find a job. It's AI's problem, or it's because of AI. I think actually just our companies aren't doing very well or managed well, and they're sort of tanking, and we're sort of hiding it. And instead of, so you get these CEOs standing up and saying, I'm freaking brilliant, I'm laying off 30% of my company because of AI, and it's like, no, if you just had a tool that made people 4 times more productive than they were, and you can't go and make your products better faster, and you're going to go and lay off a lot of people, you should be fired. All right, that's basically, it's more of an indication that your business is going down, and then they have this excuse now to go and put it under the. I think we've got real troubles in the economy. Yes, there's going to be shifts in some of the skills needed in this world. Got it? Yes, but I think that there's this is a tool. We have a new tool, and it's being applied unevenly. Any of these technologies extend the arms of man, right? It is to use an old phrase, it's gendered. Anyway, it extends and it does it unevenly. So the big corporations are going to get even more corporate and more problematic. The militaries are going to go and become more militaristic and operate with robot armies. So we know sort of where some of the real pitfalls are going to be. We in societies that are democratic still basically have to go and find the right balance for it and have industrial policies to go and have it so that the public sphere works, that we have many winners, that we have an innovation system where you have lots of companies using these tools to come up with different solutions. If we're going to end up with only 3 companies, which is looking at what it's going to happen in the United States based on bad governments and policies, we're going to have real trouble in the United States. Europe, I've got much more hope for to go and have a system of more distributed power of these tools among an innovation system that is likely to see real growth. But I think we are going to hit some real economic bumps, but be careful when people just say, oh, it's AI's fault. It's actually, there's real, honest to God, people with bad policies or bad governance or bad corporations that are doing a lot of the damage.
I mean, I don't think it's the first time we've faced that a technological advancement or evolution has affected society, and smashing machine looms and everything else to stop automated manufacturing didn't work. So I do think that what we have to become is much more literate as a public, so we know what these things are. So as more and more deep fakes come out, we have to have pressure on regulatory agencies and everything else to stop it. It's a human problem we have to solve. It's not a technology problem. In fact, the computer vision system I showed sort of there, slides from, we had facial recognition at Connection Machine, that was very easy to do because you featured, you can do it on your phone now. We can certainly do that then. But we chose not to use it. We didn't monitor everybody coming into the hallway or whatever, but we could have. So I think this is a human problem, and hopefully people will start to use AI as a part of regulatory agencies as well, being able to look through, is this real or is it fake? Has this paper been published before? Is this lawsuit have fake case law in it or not? So we have a better tool, and we all have to learn how to use it, because there will be, I think, from an economic point of view and jobs and things like that, haves and have-nots. There will be people who have access to these tools and use them as a part of their job, and there will be people who fight against it. And therefore, I think are going to lose out. And so I think it's important that we try to educate everybody and get as many people using these tools as we can, and then pressure the governments and regulatory agencies to deal with it. Enough of my soapbox.
Much of this discussion reminds me of what was said before this social media came up. I remember that people said this is great times will be coming up because people can communicate, they get access to education. It will be fantastic for Africa and all these underdeveloped countries. And nowadays we only hear problems about influencing people and fake news and regulations that are necessary. And so all this early optimism has gone. And when it comes to artificial intelligence, it is also about finding the truth. So I can only imagine a sort of competitive setup where you have a variety of artificial intelligence providers that you can ask. And nowadays, as Europeans, since you mentioned so much the Europeans should do it, you probably mean the Europeans should defend themselves a little bit from the high-tech celebrities in the United States who are running the social media in a way that sometimes is too excessive. And you know that there is a controversy between the Brussels authorities who want more regulation on the social media providers. And do you think that in artificial intelligence that will not be an issue?
I think it's just
It's just a tool. It's just a tool, and you get to govern it how you want to. And I think, you know, Europe didn't really participate in the dot-com boom because it didn't allow crawling of the web. So search engines didn't happen. So the social media didn't happen. User-contributed content like YouTube didn't happen in Europe. Those were choices that Brussels made for you, which maybe we want to turn out a little bit differently this next time around, so that things end up here, so that there's more digital sovereignty, that these technologies are actually cheap enough that you can actually do them here if you let them happen. So there's some policy issues that are holding up Europe, but there's some really positive things about some of the ideas of having European-based technology infrastructure that we actually have on this panel. So I think that there's, you can't get away from the policy angles, but I'm hopeful.
I think that validation of truth is important, and that you might use these tools that you get through AI also to do that. So first of all, I would think that much of it is positive. Me, as somebody who likes a little bit to program still, sees a lot of advantages to get, let's say, access to knowledge I could not retrieve in my lifetime, because it's spread, it's not, let's say, concentrated as I would want to have it to be concentrated. So I think we have to train the students at universities how these tools are to be used to get true knowledge and to avoid the pitfalls. Of course, you can also have wrong books. There are a lot of stupid books around that tell you stupid ideas about physics. Of course, you should not read them. So you have your professors who they can tell you the better ones, sometimes not. But this is the same here. We have to teach the next generation, or the next generation also will find out to some extent how to use it in a positive manner. I still believe in the, let's say, in the progress and in the positive thinking of human beings.
Yeah, I think we're actually at a funny point, because with AI and everything else, we've got these deep fakes, and so people now are getting very skeptical about what they read. And it used to be you would trust the New York Times or your favorite newspaper, and that would be the truth. And now that's very, very hard to define. So unfortunately, it means a lot of people, particularly in the United States, have conspiracy theories about everything. They don't believe any facts except for the ones they make up for themselves. You know, so we're at that point where I think using some of this technology to try to give factual basis for things. I've always wanted to build, you know, the thing which would be a fact checker for everything that comes in. To what I'm meaning, what does it mean to be fact checker? Well, you've got to have 3 sources from reliable things, you know, reputation-based filtering of a lot of this information. But there's a lot of questions this will expose that we haven't answered yet, that I think that we need to, as society, have an open discussion.
So, for the ending, Thomas already started. One positive takeaway message of today in one sentence.
The future's so bright, we got to wear shades.
Any more positive?
I think thinking machines and the connection machine happened, and the AI lab happened with the list machine, all of that, because it was really fun to be in that party. That I think we underestimate just how important it is to be around people that you really want to be with, that there's just a mutual love for people if you let them do it. And I think if those that create those sorts of work environments or research environments will get so much further. That's just one of the great lessons, I think, of Thinking Machines, is it's got strong alumni relationships because it just fostered community within itself, and also with the community using these and trying to make it all go. So let's go and make fun, interesting, respectful environments, and those are the ones that will thrive.
May I?
IBM, you know.
I said it to you. That virus of I could call it a virus of positivity, made it across the Atlantic to Paris, and it was almost like an infection. And you know, even though we were not aware of the impact, and you know, while we're sitting here at the time, I remember sitting with these people, and I thought, this is amazing. I don't want to be anywhere else in the world. It was so exciting, and I'm sure you felt the same way. And you know, you're asking for final words. I mean, the human factor was already mentioned. This is going to be the solution, and we have to transport that positivity to the society. We have to express it. And I don't understand why, you know, all the politicians are not every day start with that, you know, where we could be without these assholes, I'm sorry, in the world. It's not expressed anymore. The utopia is not expressed, not a utopia, but this is, and we have to do that. And because I think there will be threats too. Anyway, we want to be positive.
My message is the same, just in different words. I mean, we should really support startups. Young people who have good ideas must be supported. And that is what you did.
We got great support.
Yeah. And we must do everything we can to keep that going. And not rely on these very big companies that sort of take up more and more business, independent businesses. There's a certain big danger. If you walk through German towns, you see many empty spaces, which was small business, and it's now Amazon. It's somebody sitting in California and dreaming to go to Mars or wherever he wants to go. Okay, you can say this is progress because things have become easier, but they have grown on the possibilities that computing has offered them.
Let me double plus on that one, if I could. Okay. And some of the things, listening to Thomas, the historian, go and talk negatively about some of the things that I think we did really right, where Licklider made it so that we had an open playing field, which was the internet. You could plug in, anybody could plug in. It was a permissionless world that you could go and plug into, and then you were part of the internet, and it spread like wildfire. That we made it possible to go and set up shop on this internet without permission. It didn't have to go through Apple Store to go and allow you to do that. Like, screw that. No, it was a government-oriented structure. Yes, it was funded by ARPA. Thank God. And because it made a system that lots of people could win at. That they could be a small business and grow. We tracked the growth of these little websites, and they were unbounded except by their own ideas. That's how you make things work. And it did work for a while, and now we have these very large companies controlling way too much, and it's keeping down a generation that feels kind of helpless. So I'm with you, and I think we did a bunch of things right in the United States with the internet, with the web. I mean, okay, that's Tim, came from CERN, right? But it was. We did a lot of protocols, not platforms. We stood up for the little guys, and times.
Open source is one.
Free and open source software. Stallman was right. And so let's go and find the next generation of that. Because right now, if we go to just having a few big things that you have to go and bow before, we're not going to have that kind of growth, and we're going to have a stunted generation.
This means we have to educate the next generation. As a professor at university, I make the experience, if I have a fascinating topic like quantum computing, I have 100 students from computer science sitting there. How comes? Yeah? This is very encouraging. And what we have to do is we have to teach everybody that they don't just admire stupid pictures from Grok, but use Grok to do good programming and create progress. Yeah? So we have to teach them how to distinguish between nonsense and between interesting things.
Yeah, no. Yeah, so thanks a lot for all of you. That was an interesting and also vivid discussion that we had. I think we all get a lot of impressions now for the past, of course, but also for the future. Yeah, thanks a lot also for the audience staying here for quite a long time. And yeah, I wish you a good evening.
And I want to put in a last word thanking Michael Beigel for saving my machine, our machine, for contacting Alistair, for Alistair immediately saying, oh my gosh, this is a great idea. For Daria, through thick and thin and ups and downs, and oh my God, we have no funding, and where can we find it? How many people are actually going to be able to come to speak? We don't know, about 3 or 4 of them, and it's a week away. And for Hannah sticking in there with us and doing this all, for Max's film that's running out next to the left of the connection machine, for Daniel, I'm so bad with names, am I getting your name right? Who set up that really beautiful enclave there with the connection machine, the data vault, the front end, and the various interfaces, for Philipp Leopold, who took time off from his PhD to make the thinking machines come alive, and I hope you still give him his PhD, and for making that wonderful interface that for the first time lets visitors actually play with the machine. And I've been saying over and over again, this is the conference I've been wanting to hold for about 40 years, which means from the time the first connection machine was launched, when I also soon after that realized that no one understood my design, and I had to describe it and say, well, actually, it's not just decoration. I'm trying to convey something with lights. And lots of people understood that, but they couldn't formulate it beyond saying, oh, it's really cool. It's got all these blinking lights. So thank you. Really cool. It's got all these blinking lights. Yeah, him, for instance. So, and for all of you who went on this journey of discovery with me, for Klaus Schilling, for Thomas Lippert, for Heiner Igel, for David Lloyd Owen out there, and Terry Dontier, hello, for connecting us with Klaus and Thomas, and really underscoring my impression from talking to Danny, from Rooster and Lou, that no, it wasn't a failure. Thank you all from the bottom of my heart.